Sustainability, that is GSIS 2020, organized by the Department of Metallurgical and Materials Science Engineering in NIT Durgapur. Now, India is the second largest steel producer of the world and aiming to produce 300 metric ton of steel by 2030. For achieving the target, production of major breakthrough is required in technological intervention. Sir, it's already started. And the proper energy and environmental management to make the steel production sustainable. The three E's that is very required in this near future is the good environment, lower energy and better economy. These are very important for steel making, and now today's topic is this crucial topic of our discussion.
Our department has taken up crucial topic like this and has organized so many conferences, workshops, talk sessions, and many more programs so far. But now, due to this COVID-19 pandemic situation, we are not able to gather up. We have now have to be home and be safe. Hence, it is our humble endeavor to organize webinars and interact with renowned personalities from all over the country and abroad. The aim of this webinar is to provide an understanding of energy and environment management in metallurgical industries towards sustainable steelmaking among the academician, researchers, industry personnels. Let's hope we have a successful session, and without further delay, I would like to request our HOD as well as Chairman of GSIS 2020, Dr. Madan Mohan Ghosh sir, to say few words regarding our department and recent activities.
Please, sir.
Over to you, sir.
Thank you, Satodipa and Rishikesh. Good afternoon to one and all, respected all dignitaries present in the inaugural ceremony today. Mr. A.V. Kamlakar, CEO, ISCO Steel Plant, Durgapur Steel Plant and Alloy Steel Plant. Mr. Lohitendu Badu, Secretary, IIM Local Chapter at Durgapur. Professor K.C. Ghata, Chairman, Institution of Engineers, India Local Chapter Durgapur and TQ Coordinator of NIT Durgapur. Professor S.S. Thakur, Dean FW, NIT Durgapur. The speakers, all participants, my colleagues, students, scholars, ladies and gentlemen. On behalf of the organizing committee of today's international webinar and the whole metallurgical and materials engineering family of NIT Durgapur, I welcome you all to this webinar. Thanks to our institute authority for providing all sorts of supports for organizing this program. This program is organized by our department in association with the newly formed Students Chapter of Indian Institutes of Metals at NIT Durgapur. In this connection, I am happy to announce here that the Indian Institute of Metals, which is the largest professional body of metallurgical fraternity, have approved the formation of a Students Chapter here at NIT Durgapur. The formal inauguration of this Students Chapter will be held soon, and I must thank Mr. Badu, Secretary of IIM Durgapur Chapter, who is employed in DSP, General Manager in RCL Lab, who is present in this online, who is also present in this online inauguration program. And also my colleague, Dr. Arup Kumar Mondal, for their constant support to form this Students Chapter here. From now onwards, we can organize different programs, seminars, events, etc. here in association with the Students Chapter. We are happy to have Professor R.C. Gupta, retired professor of IIT BHU, India, and Dr. Naushad Haq, senior scientist, CSIRO, Melbourne, Australia, as our speakers in today's webinar. Both of them are renowned in the field of today's webinar and have handled different projects, responsibilities in this area. We are really thankful to both of them for coming forward and accepting our invitation. I express my hearty and warm welcome to Professor Gupta and Dr. Hawk to this webinar. And my heartfelt thanks to all the coordinators, both the coordinators, Dr. Arup Kumar Mondal and Dr. Sotodol Gorai, for that effort to organize such a program. And I encourage all my colleagues to organize such kind of events in future. This kind of function will enlighten our department and our institute. The topic of today's webinar, Global Steel Industry Sustainability, is very relevant in present scenario, particularly for the country like India. We all know that India is now the second largest producer of steel. As of now, India produces around 110 million tons of crude steel. As per the National Steel Policy framed in 2017 by Ministry of Steel, Government of India, India is targeting to produce 300 million tons of crude steel by the year 2030-31. A major part of Indian economy depends on the steel production, and so increase in steel production rate will lead the economic growth of the country. Steel is so important that the per capita consumption of steel is taken as the indicator of economic growth. This has become even more important in the present situation of COVID-19 pandemic and the consequent economic breakdown of the country. The engineers, particularly the metallurgical and materials engineering fraternity, have a great role to play to achieve this target. The major concerns to achieve this target are the environmental issues and energy economy. We like to reach to the target with minimum energy consumption and of course without hampering the environment. This is very challenging and industry and academia should join their hands to achieve those targets. In this context, I, being the head of the Department of Metallurgical and Materials Engineering of the of an institute of national importance like NIT Durgapur, take the advantage of this platform and request Mr. Kamlakar, CEO of the ISCO Steel Plant, who is also in additional charge of DSP and ASP here, who is now looking after all the three giant steel plants present in and around Durgapur, to take initiative to form effective collaboration between NIT Durgapur and cell steel units that he is looking after. This is the need of the time, and our institute is competent enough and have very energetic and knowledgeable professors in our department and other departments of the institute, and will be happy to contribute to these collaborative works. My own perception is it is preferable and better to solve some local problems locally. I know there are problems which these units are facing, like utilization, waste disposal and utilization, energy and environmental management, etc. Apart from some process related problems, which I suppose can be solved locally in a collaborative mode of study without taking help of any external agencies. I can see how much relevant that today's topic is, as reflected through the overwhelming response from the participants. From the last report I obtained from the coordinators, this webinar has been registered by more than 750 participants from more than 50 countries all around the globe. My heartfelt thanks to all the participants for their interest. I hope this webinar will be extremely beneficial to the participants, and I wish all success of this program. Thank you all.
Thank you, sir. Thank you so much. We are really very glad to be a part of such an endeavor. Thank you so much, sir, for your kind words. And now, I would like to request Coordinator of GSIS 2020, Dr. A.K. Mandal, sir, to please brief something about the program and share a few words with us. So please.
Thank you, Satadipa. Before starting my lecture, I want to uh, request our chief guest and speakers to make video on so that we can see their face. Am I audible?
Yes. Yeah, now it is audible.
Yeah.
You are muted somehow.
Yes. Respected chief guest, Mr. A.B. Kamlakar, sir, CEO of ISCO Steel Plant and additional charge of CEO Durgapur Steel Plant and Alloy Steel Plant. Respected Director Sir, Professor Anupam Basu Sir, respected Professor S.S. Thakur Sir, Dean Faculty Welfare, NIT Durgapur, along with uh, two respected personalities from two professional bodies in institution of from institution of engineers, chairman of institution of engineers Durgapur local chapter, Professor K.C. Ghata sir, and institution of Indian Institute of Metals Durgapur chapter secretary Loitendo Badu sir, and respected speaker Professor R.C. Gupta sir, as well as Dr. Nausad Haq sir. I welcome all of you. It is my privilege to organize such international webinar on a crucial topic of global steel industry sustainability GSIS 2020. This topic is more relevant as our HOD sir already told that we are targeting to produce 300 million tons crude steel by 2030, and lower energy consumption as well as the lower environmental degradation can make the steel industry sustainable, which is our theme of this webinar. I am happy that to address these burning issues, more relevant issues, two personalities are present here. I am also happy after showing the response. It is sir had already told it is 750, not it is near about 780 80 participants from uh, 17 countries, and more than 70 participants from abroad, like Afghanistan, Algeria, Australia, Bangladesh, Bolivia, Ethiopia, Hungary, Indonesia, Malaysia, Myanmar, Nigeria, Philippines, Sri Lanka, South Africa, Mexico, United Kingdom, and many more. We have got response from almost all IITs and NITs, as well as public and private industries like SAIL, Tata Steel, JSW, JSPL, Ispat, ArcelorMittal, NMDC, and many more, and also from the research organization like NML, IMMT, etc. So I hope all participants will be benefited from this webinar. Thank you.
Thank you, sir. Now, I would like to thank Dr. A.K. Mandal, Coordinator, GSIS 2020, and now I would request Mr. Lohitindu Basu,
Badu.
Secretary, IIM Durgapur Local Chapter, to say a few words. Sir, please. Mr. Lohitindu Badu, sir.
Sir, maybe we will listen to Lohitendu sir after a few while. But now I would like to request Professor K.C. Ghata sir, who is chairman of IEI Durgapur local chapter and also our very dear Professor K.C. Ghata sir.
Can I start? May I start? Hello?
Yes, sir. Yes, sir. Make your video on and start your speech.
Yes, I have my video is on.
Okay.
Okay.
Okay, sir.
Okay, sir.
Okay, sir. Thank you, sir.
Thank you,
Start.
sir.
Chief guest of today's international webinar on global steel industry sustainability, Mr. A.V. Kamalekar, CEO DSP ASP ISP. Eminent speakers of the program, Secretary, I am local chapter, Mr. Mohsin Badu. In faculty welfare, Professor S.S. Thakur, Head of the Department, Dr. Raymond Ghosh, Coordinator of the program, participants from academic institutions, industries, researchers. It is indeed my great pleasure to address you as Chairman IEI Durgapur Local Center. It is a matter of proud that Department of Metallurgical and Materials Engineering NIT Durgapur has arranged a program on such a topic which is the call of the hour and being organized in Steel City. It is also delighted to note that this webinar has received overwhelming response across the world to attend. We all are concerned about energy, economy, and environment. I think there are serious attempts also from all the corners of the academic institutions and industries to explore and implement the technologies to make the process industries energy efficient so that the production will be economically feasible and finally we can make our environment green and pollution free. Steel industries are heavy industries which are energy intensive, involve hazardous processes and found there are a lot of possibilities for polluting water and air. But technological advancements have been capable enough to overcome such type of problems and we find there are clean and green technologies for steel manufacturing which are already in place. Simultaneously, we need to make the process sustainable because of intense competition worldwide. Naturally, all those matters are expected to be discussed and deliberated by the speakers with the large pool of vibrant participants. Institute of Engineers India is a statutory body to promote and advance the engineering and technology. It is the largest multidisciplinary professional body of engineers encompassing 15 engineering divisions with the corporate membership of more than 2.2 lakhs and hosts national convention each year for all 15 divisions on emerging areas of science and technology. IEI is now celebrating its centenary year through different programs. IEI has its headquarters located at Kolkata with national presence through more than 100 centers and several overseas chapters, forums and organs. II therefore provide the platform for effective interactions and brainstorming sessions and deliberations of professionals from academics and industries, resulting the outcomes or implementation to their respective fields. Also extends the essence of scientific and technological development to the greater society. Many thanks to the Department of Metallurgical Materials Engineering for inviting IEI Durgapur Local Center for this program. I wish the great success of this program and thanks to all for the patience hearing.
Thank you,
Hello,
sir. Thank you so much,
hello.
sir.
I'm online again. I'm El Badu.
Okay, sir.
I'm online.
Yes, sir,
Yeah.
Lohitendu, sir.
Yeah,
Sir,
Sir.
you
he
please
has
start
he
your
has
Okay,
joined,
sir.
please. Yeah.
speech.
Okay,
Okay. Okay.
thank you, Professor Ghata, sir. Now I would again request Mr. Lohitendu Badu, Secretary IIM Durgapur Local Chapter, to say a few words. Lohitendu, sir.
Okay. Okay. Thank you
Please
very
make your
much.
video on. Yeah.
Yeah. Thank you very much. Respected Sri A.V. Kamlakar Sahib, Chief Executive Officer, ISCO Steel Plant and Durgapur Steel Plant and Allied Steel Plant, Steel Authority of India Limited, Professor Thakur Sahib, Dean NIT Durgapur, Professor Nanta Sahib, NIT Durgapur, Professor and Dr. M.M. Ghosh, HOD of Metallurgical Engineering Department, NIT Durgapur, and Chairman of this organizing committee of Global Steel Industry Sustainability 2020. And Dr. Mandal, he is the coordinator of this international webinar, and distinguished delegates and participants from all over India and world, comprising educational institutes like IITs, NITs, and also other institutions, industry experts from SAIL, Tata Steel, JSW, and others. And my very dear students from NIT Durgapur, particularly Metallurgical Department.
सर अभी ये आरओडी तो सही है ना सब?
We are here and extremely
वन
thankful for the webinar
अच्छा
and what proceeding this
और
very
मतलब
important GSIS 2020. Today, it is a momentous day for both NIT Durgapur and Indian Institute of Metals Durgapur chapter. We have been trying hard since a long time to forge an alliance with academic institutions of national repute, particularly with NIT and other engineering institutions in this part of India, with a special emphasis on involving students of the institutes. Indian Institute of Metals has been leading in this area and successfully organized many seminars, technical e-talks, events, and discussions in which NIT students from Metallurgical Department took active part. To bring more cohesiveness and synergy in working, we thought of starting a student chapter in the institute itself. And after doing this international event was the first ever attempt, an example of such successful collaboration and joint working. Ladies and gentlemen, students are future of our beloved nation. Without their participation and involvement right from a very early stage, effectiveness in disseminating and imparting education seems difficult and also very counterproductive. That is why such platforms involving academia, industry, research institutions, student bodies, and forums like IIMs meet and discuss global as well as local issues concerning to industry from time to time to find out solutions to emerging problems and challenges. In this perspective, I would say NIT Durgapur in general and Metallurgical Department in particular are doing fairly an excellent job in bringing industry, academia, and students together and organizing many events in this regards. Thank you very much to our HOD of NIT Durgapur Metallurgical Department and Dr. Mandal. In this respect, I would definitely agree that role of DSP and CEL has been instrumental in achieving this cause. Therefore, we are immensely thankful to our CO Sahab, Sri A.V. Kamlakar Sahab, who is the CSP and ISP and ASP for unstinted support and guidance in this aspect. It is quite heartening and admirable to note that the webinar topic has been extremely relevant and appropriate considering the current pandemic crisis situations that has thrown many challenges in each and every sphere of activities today. At the same time, we feel extremely proud to be associated with NIT Durgapur, particularly the Metallurgical Engineering Department, in organizing this international event to benefit students, academia, industry, and research bodies alike. I am sure students will be able to take benefits of being members of this very prestigious body like IIM and its many platforms and many programs being conducted from time to time throughout the year across the country and abroad. We will appreciate that IIM has huge number of benefits, especially for the students. Last but not the least, I wish the program a grand success and strongly hope the synergy of IIM and NIT will bring many more fruitful ventures in the coming days ahead for the benefit of metallurgical fraternity. Thank you all.
Thank you, sir. Thank you so much for such words. And is we will now request Professor S.S. Thakur, sir. Is he online? If you are online, Thakur, sir, then
Yes, I
I
am
would
online.
request. Okay, sir. So now, thank you so much, Lohit, sir. And now I would request Professor S.S. Thakur, sir, who is Dean Faculty Welfare of NIT Durgapur, to please share a few words with us. So please.
Head of the Department of Metallurgical and Materials Engineering, Professor R.C. Gupta, Dr. Namusad Haq, other dignitaries, faculty members, participants, ladies and gentlemen. A very good afternoon to
all of you. I am really honored to be present to this international webinar on global steel industry sustainability, GSIS 2020, organized by the Department of Metallurgical and Materials Engineering in association with the Indian Institute of Metals Student Chapter NIT Durgapur. The meaning of the word webinar, although known to us, was not commonly used in recent past till this pandemic situation came due to the COVID-19. The seminars, talks, FDPs, conferences which used to take place earlier in physical presence are now being organized over the internet in virtual mode. NIT Durgapur has also coped with the need of the present situation. Faculty members are now participating in these programs through MS Teams, Google Meet, Zoom, etc. Further, NIT Durgapur has also started organizing such programs. Particularly, I'd like to mention two of such programs which are being held in addition to this particular program GSIS 2020. One by the Department of Chemical Engineering, the 8-day online industrial workshop on bridging the gap between the chemical industrial process challenges and chemical engineering curriculum from 17th instant, and it will continue up to 8th proximo on every Fridays and Saturdays from 8 to 9 p.m. The other being the series of webinars organized by the Department of Biotechnology on 1st, 4th, 10th and 18th of August 2020. The programs are being addressed by erudite persons not only from India but also from abroad. About today's program, sustainable development is a buzzword for any manufacturing industry and iron, and steel sector is no exception in this context. I understand there are three major aspects of sustainability. Number one, to save the natural resources for the future generation, a very important aspect of sustainability. Number two, to keep the pace of development and to meet the current demand, that is production has to be increased to meet the demand. Number three, to comply with the environmental norms and regulations to save the environment. It is to be remembered that during the Paris Climate Change Conference in December 2015, governments worldwide have agreed to international climate policy to aim to limit the increase of global mean temperature to less than 2 degrees centigrade. This means we need to reduce the emission of greenhouse gases and CO2 in particular. But CO2 emission is inevitable for iron and steel production technologies on account of use of fossil fuels. Thus, it appears that these industries are major contributors to CO2 emission. Therefore, they have the responsibility to reduce it through improvement of energy efficiency, recycling and reuse, development of new technologies and rapid commercialization of these methodologies, carbon capture and storage, etc. I'm an electrical engineer and my specialization is power systems, so I'm not an exponent to these fields. I believe that eminent speakers of this webinar GSIS 2020 will certainly address these issues. I expect all the success of GSIS 2020. Thank you all.
Thank you, sir. Thank you so much for your kind words. And of course, we would make it a success. Of course, we would. And now I'm very happy to announce that we have our chief guest, Shri A.K. Kamlakar sir, who is CEO of DSP, ISP as well as ASL, and he is the chief guest of our inaugural function. And we have had him for a few occasions now. He had shown us tremendous support. Our department is really, really very glad and very honored to have you with us, sir. Welcome you. I, on behalf of our department, welcome you heartily. Thank you again for supporting us all the time. I have the opportunity to introduce Mr. Kamlakar sir. So I would do that. It's an honor. Sri Kamlakar sir is CEO of ISCO Steel Plant since 1st June 2019, with additional charges of CEO Durga.
Unmute, Satadipa, unmute.
Yes, sir, I did. Someone is muting me again and again. Can you hear me?
I am requesting all participants don't unmute other.
Okay, so am I audible, sir?
Yes, now audible.
Okay. So I would say again that he is the CEO of ISCO Steel Plant since 1st June 2019, and he's the additional in charge of CEO in Durgapur Steel Plant and Alloy Steel Plant Durgapur. Prior to this, he was holding the charge of Executive Director of Cell Salem Steel Plant with additional charge of MS Visheshwaraya Iron and Steel Plant, Bhadrabati, Karnataka, a unit of SAIL. He is also the board member of SAIL Refractory Company Limited, Salem. He's basically a metallurgist, completed his BE in metallurgy from Government College of Engineering and Technology, Pandit Ravi Shankar Shukla University, Raipur, and joined Bhilai Steel Plant BSP in 1987 as a management trainee. Certified black belt in Six Sigma, Sri Kamlakar is over 3 decades of experience in operation and administration of different areas of integrated steel plants. He worked in various capacities at the rail and structural mill of Bhilai Steel Plant for over 2 decades. He has received a patent for design and successful production of asymmetric rails. In 2016, he has moved to Durgapur Steel Plant, where he was General Manager IC Mills and later General Managers Mills, Wills and Axle Plants. He was instrumental in successfully changing the input material of merchant mill. He has visited many countries for training as well as leading various teams for technical discussions and etc. Organizing committee, on behalf of our organizing committee, I'm very proud and very happy to have such a personality, such an experienced person as today's crucial topic. We are very proud and happy to have him today. So now, Mr. Kamlakar sir, I would request you to please share a few words with us. And thank you, and I again welcome you heartily to join us today. Thank you, sir.
Thank you.
Sir,
Am I audible to all?
I request, yes, sir, I request you to make your video on. Yes, sir, it is visible now.
It is on. Video is
Yes.
already on all the time.
Yeah, okay, fine,
Okay,
fine,
okay,
fine.
sir.
Okay. Okay, no issue. So once again, thank you for to NIT Durgapur for organizing such a nice webinar. And aptly this topic on global steel industry sustainability. This is a very, I think it is a very burning topic nowadays because just last week I was attending a webinar on rolling of flat and long, where the joint secretary, Secretary Steel, and all the eminent speakers of Tata and JSPL, Sharmaji was there from JSPL, and everyone was there. So I was just going, I was the speaker in that seminar also, webinar rather. So I was just finding that yes, steel is nowadays this is the only product which can have a better sustainability than any other metallic products, and rather it will now it is doing a fierce competition with the non-metallic products also because of its very unique quality, like it can be reused and recyclable, and that is the need of the hour. And though the because the steel has got this very unique property in it, so now we are finding the very much use of it. But you see, the energy and environment are the most challenging issues in the modern steel production. Actually, the concept of this sustainable steel imposes industry for better energy and environmental management due to the strict legal framework. As you know, this Asansol and Durgapur belt is falling under a red zone as per the environmental norms laid down by the West Bengal government. So the government is very much keen on seeing the conditions of these industries and to see that how they are working with the sustainability. Initially, this sustainability word, we generally foresee that it should be a consistent profitability, consistency in working. But now the sustainability means it is the sustainability as with respect to the energy as well as the environment. That is the usage of the optimum utilization of the resources, the total effect on the environment aspect impact study of every activity what you are doing for making the steel. So that is the okay, okay, but
Fine, it's fine.
I am not able to see it. Okay, sorry. So this is the sustainability what the government is looking from any steel industry. So at present, whatever new projects are coming, everywhere it has been taken care that apart from the all the production and the financial, this sustainability to the environment as well as to the energy is taken care. So currently, as it is already mentioned, but as a repetition also, I just wanted to mention again and again that we are at present producing 110 million ton, as you know, and we are marching towards 300 million ton. So that is a gap of 190. So we will be having a very new projects coming in all the steel industries across the country. I'm talking about the country. So the key points of the national steel policy is the globally competitive industry. That is, the steel industry should be Indian steel industry should be globally competitive. As per the now, the latest government policy, as you are all aware, that imports has been now stopped. Less than 200 crores, you cannot go for the imports. The areas which are contained with the defense issues, you cannot buy anything from those. So this has posed a big challenge for the industries across the country to be make a Atmanirbhar Bharat, what is our honorable minister has said. So with that Atmanirbhar Bharat, a lot many steel industries are coming, and for them this is the big challenge that how to have a sustainable production from these industries. Our per capita consumption at present is a very low. Now we are aiming to reach 160 kg per man per. But you see the some industries now in if you see the ISP where I am heading now, our manpower productivity is very high. It is almost 500 kg per ton per man per year, which is the highest in the sale. So these are the things which are now becoming a benchmark figures, and which are the figures now it has been monitored rather than how much you are producing the steel you are producing. It is the cost per man per year. It is the per capita consumption per man per year. It is the manpower productivity per man per year. It is the carbon emissions, CO2 emissions. These are the things which are looked by the all the legal framework of the country. So we have to be very much competitive on it. Indian steel industry wants to become a world leader in energy efficient steel production with a environmentally sustainable manner. Indian steel industry, the domestic industry wants to be a very cost effective and quality steel producer. Attaining global standards in the industrial safety and health. That is another big challenge. For safety, you must be hearing daily some of the incidences happening in the industries. Maybe in the steel industry, maybe the peers which are working with the steel industry. So this is a big challenge for us, and the sustainability, substantially reducing the carbon footprint of the steel industry. So these are the big challenges, and the another challenge what is coming to the steel industry, that is the utilization of the low grade raw materials, because India is not so much rich in the high quality raw materials. We are mostly depending upon the our imports, but now because of this constraint, the low grade raw materials is the one important where you we will be doing the mining. So again the global against the environmental issues may come, but this is again a one challenge what we will be having. We are having a lean ore, particularly for the steel, lean iron ore, and high ash coal, and which is a very harmful for both the things are very contradictory for any steel industry. So this has become a very challenge for the all of the Indian steel industries. Apart from this, the imposed restriction on the global in the environmental issues, uh, the steel industry is a major contributor to global CO2 emissions. And the World Steel Association has indicated that this is to be 6 to 8% of the total emissions. It means that the industry has a large incentive decrease energy usages and thereby reduce the production cost. Therefore, the international steel industry has accepted the challenge to cut net CO2 and other greenhouse CHG emissions by 50% or more in the coming years. So this is a challenge imposed on the Indian steel industry also, because the Indian steel industry has to fall in line with the global steel industry in order to become a competitive in the cost as well as the energy. So we are going with the new technologies like ULCOS, that is the ultra low CO2 emission steel making technology. So my request to our NIT team that if it is possible to incorporate such kind of courses in the our curriculum, because this ultimate reduction in the steel making process by innovative technology like for Cooler 50, these are the projects which are coming up highly in the globally, and we have to be our engineers, the upcoming engineers should be sufficient, self-sufficient to have this technology, at least as a knowledge of this technology, so that they can implement them in the future. So the steel plants are gearing up with these technologies, and the main thing, because I have worked in the Salem steel plant, which was designed with ZLD, zero liquid discharge. There is no discharge of water, no discharge of any liquid or any emission coming out of the plant. It is a total green plant. And now this concept has to be there in all the new industries. So the ISP ISCO steel plant, which is the modernized in 2015, we have got most of the technologies available with us to continue to contain the emissions. Durgapur steel plant also, we are now going for the secondary emission control systems in the steel making, that is a doghouse technology, and some controlling the fugitive emissions in the SMS converters, which maybe we'll be doing in the August month, starting from the August month with the SMS Mir Germany collaboration. So we have got the ZLD in Durgapur maybe around after 2 years, because there is an old plant, so we'll be putting the ZLD. We have got online continuous emission and effluent monitoring system, which is the now it is the need of the hour, because all the data are transmitted online to the West Bengal Pollution Control Board, and they are monitoring these things from the online. So it is a mandatory for all of us, and so we are doing it. So I hope that this webinar will become a very successful, and it is a very apt time that NIT has organized this, and I am looking forward from a very informative speeches from our eminent speakers who are here, who have got a very rich experience on this field, and I wish that all the students as well as the industrial counterparts who are attached with this webinar will be much benefited from this. I once again thanks NIT Durgapur for holding this webinar. Thank you. Thank you.
Thank you, sir.
Thank you,
Thank you
sir.
so much,
Thank you
sir.
so much, sir.
So thank you for your sharing your enormous experience with us, and importantly, your practical experience is worth listening to and remembering. Your message will be with us, sir. Thank you, sir. And
Thank
now
you.
let's move forward. Now I would request Coordinator S. Ghurai, sir, for delivering vote of thanks. Professor Ghurai, sir.
Okay, thank you, Satodipta and Rishikesh. A very good afternoon to everyone. On the behalf of organizing committee, it is a great honor and privilege to deliver vote of thanks. Today, my words are not enough to express the gratitude. On the behalf of organizing committee, I would like to thank our guest, Mr. A.V. Kamlekar sir, who spared his precious time for of us and graced us with his thought-provoking address which set a part of movement. I would like to thank our director, Professor Basu, who could not present in this function for organize such type of events. Thank you for listening. Professor S.S. Thakur, Dean Faculty Welfare of NIT Durgapur, we are grateful to you, sir, for readily accepting our invitation and for being with us today. Thank you for your all of wisdom. Our sincerest gratitude to Professor K.C. Ghanta and Mr. L. Badu, head of two professional studies of for being with us today and sharing your views. We have two eminent speakers for this Dr. Naushad Haq, CSIRO, and Professor R.C. Gupta, IIT BHU. Words fall short when I try to express my sincerest gratitude to thank them for accepting our invitation to deliver lecture here. We would like to thank all the participants for showing their interest for this program. I hope that they will enjoy it and enrich their knowledge. Special thanks goes to our HOD, Professor M.M. Ghosh, and all faculties of our department who always stand by us, guide us, and motivate us. We feel proud and thank you for your presence in this function. I will fail my duty if I do not mention that we are fortunate to have a team of very motivated and dedicated students like Pranav, Shubhadeep, Sayan, Bhupesh, and Orijit Maji. They are particularly involved in streaming of this program on the social media platform. We appreciate your effort. And of course, Shatodipa and Rishikesh, thank you for your nicely conducting the program. I once again thank you and have a nice day. Thank you.
Thank you so much, sir.
Thank you, sir.
And now, with the end of inaugural session, we will start the technical session. And before that, I would like to say a few words about our next speaker, Dr. Nashad Haq, Senior Scientist, CSIRO Australia, for his presentation. I have the opportunity to introduce him. Dr. Nashad Haq coordinates undergraduate courses on mineral processing, Monash University, Australia, on sustainability and life cycle assessment from Swinburne University, Australia, and offers lectures and workshops over a decade and co-supervised 10 PhD students to completion. Currently, he supervises 3 PhD students. He has been a guest lecturer at multiple universities. Dr. Huck manages several high-level intergovernmental scientific collaborations and is the leader of the MOU signing between large multiple research organizations, government science agencies, ministries, and universities. Dr. Huck had been awarded a PhD in chemical engineering from the University of Sydney in 2002. Dr. Huck is an elected fellow of the Australasian Institute of Mining and Metallurgy, Australian Institute of Energy, and the Institute of Materials, Minerals and Mining, UK, and was a director of the board of the Australian Life Cycle Assessment Society for 10 years. His current focus now as a project leader to develop techno-economic and environmental modeling tools using LCA for future multi-billion dollars hydrogen energy system in Australia. Dr. Huck has extensively studied LCA of a variety of metals including aluminium, magnesium, ferroalloy, gold and nickel to identify opportunities for CO2 emission reduction. With now I would request Dr. Huck sir to please start his talk for today. So over to you, sir, Dr. Huck sir.
Thank you and good evening from Melbourne. Thanks for the introduction and your kind words. Can you hear
Thank
me
you, sir.
well, by the way?
Yes,
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 sir.
yes,
sir, we
yes.
can. We
Good,
can.
thank you. So actually just now, in Melbourne, curfew has started outside. So essentially we cannot go outside. So after coming in Australia, this is the first time we heard the word called curfew. Unfortunately, this is a very difficult situation, COVID-19. And in Melbourne, we were doing very well, but just our number of new infection were going up. So that's why the government has imposed new restrictions from tomorrow, actually tonight. So in the morning, we will probably have a lot of restrictions. So yeah, we hope everyone is safe and sound wherever you are, and around the world. We know it is a very difficult situation and circumstances, so hopefully that will over. But this is the health aspect. But another aspect, our speakers in the beginning, particularly, I'd like to thank Dr. Arup Mondal for inviting me here, and Dr. Ghosh for introducing. And I mean, as you said, that 3 E's very nicely put: energy, economy, and environment. So whether health issues around the world is happening, we know the pandemic, but at the end of the day, the economy has to go, and we need to have the economy going, and obviously energy and environment, climate change, all these issues, sustainability, our previous speaker spoke about. So those issues will be there. So we need to work on that, and steel is one of the sustainable material, as was told by our CEO. So I'm going to share my screen. Hopefully, let me see how that works. Can you see my screen?
Yeah.
All right. So thank you once again for inviting me. So next 40 minutes, 50 minutes, we'll be discussing about life cycle based environmental impact of iron and steel making. So hope you can follow me. So I'm going to talk about introducing myself and the organization I work for, some of my experiences, and then I will introduce the topic life cycle assessment. We spoke about sustainability, but to determine sustainability and sustainable indicators, life cycle assessment is one of the tool that people use for making essentially what are the sustainability of a system. Life cycle assessment is one of the way to do that. And at the end of the day, how to do it, what are the results when you generate, what do they mean, and I'll make some conclusions. And obviously, I understand that a lot of interest going on in hydrogen area. I will probably touch a little bit on that area. So just I've been introduced, but I don't want to spend a lot of time here because I've been introduced already. I originally, by the way, come from, if you draw a straight line from Durgapur to Nodia, Bardhaman, and just across the border, I grew up in Karpas Danga, which is probably 20 kilometers or maybe 15 kilometers from Nodia, other side of the border. I have still my relatives live in Nodia area. So Krishnanagar, essentially, I'm talking about Nodia. So I come from there. I grew up there, but I left Bangladesh for a long time ago. I went to United Kingdom for doing my master's, and then moved to University of Sydney for my PhD. I moved to New Zealand. I worked for a government research institute or research organization like CSIRO in Australia. It is like your CSIR in India, essentially the CSIRO. So I'm here in CSIRO after moving back from New Zealand to Melbourne 15 years ago. So I'm sort of now, as I was introduced, my interest in teaching, and that's my sort of hobby. Although I'm a scientist, essentially, I introduce myself as a researcher. And at the end of the day, I do a lot of international activities and research collaborations, PhD student supervision, and keeps me busy. So who CSIRO is? Essentially, as I said, it's like your CSIR in India. We have got multiple laboratories around Australia in various locations. Brisbane, Sydney, you can see in the map probably. So I come from Melbourne. As I said, the Victoria is not very good situation at the moment. Particularly Melbourne is a hotspot in terms of COVID. But we have got labs here and within Victoria. We have got around 60 locations around Australia. But majority of the capital cities, as you know, Sydney is the capital of New South Wales, Brisbane, and Perth. And you know, Australian capital is Canberra. There was a fight between Sydney sider and Melbourneians. So they said, okay, we will do sort of halfway. It is towards Melbourne. So CSIRO is sort of Australian National Research Agency, Science Agency. So some of our invention, if you use Wi-Fi, probably I acknowledge and I thank my colleagues who developed this. You probably Google it. We got about $1 billion from this invention, although our colleagues didn't intend to invent it, but they eventually made an algorithm which made Wi-Fi possible. Also, we have got plastic banknotes. Many of the countries are using it, and you can see probably the longevity of the money or currency that increased because of the plastic notes. We have about 5,500 plus scientists working in various sites, as I said, and we have got $1.2 billion plus budget every year. We have a lot of PhD students, postdoctorate fellows, postdoctoral fellows, and also our own work. So we generally work or do research and technology development for industries funded by Australian government and also industries and also some international activities we have got. So who I am in terms of speaking about life cycle assessment, which will be my focus of this today's study. So we have published and working in this space for a while now. So I lead a team on life cycle assessment, and we have published some papers, and a lot of our papers are cited by other people. So hope we are doing good work, and that's why probably it is cited, and that is one of the satisfaction when you do publish papers. So I have quite good interaction with India because of, and we had a nice time in Durgapur NIT, and probably I couldn't see some group photos, but at least one photo I planted a tree with our colleagues also. So that was fantastic time. We were looked after very well, and that was in probably last year or year before, and then we went again for the conference. I also involved with Ministry of Mines in India. I was some involvement with. I think the secretary and also the Steel secretary recently visited Melbourne, and CSRO I facilitated, and we had some discussions. And some of the officials in Ministry of Mines in India. We also visited some of the mine sites. I was part of a delegation from CSRO. I was selected, which was led by the then trade minister Stephen Chobo from Australia, and also Professor Firoz Alam, who probably you know a lot of our colleagues that we traveled together last time to Durgapur. So I think I'm going to talk today about the process evaluation technique. That's what we use for both life cycle assessment and techno-economic evaluation. So essentially, the technique is that you need to develop a flow sheet, and you need to undertake mass and energy balance. Those who are familiar with chemical engineering principles, and then you need to list the equipment, size the equipment, and understand the capital cost and operating cost, and you can have that one. But at the same time, those inputs can be used for life cycle assessment. What it is, I will be talking quite a bit about that anyway. And what's the purpose of that? Once you know, and obviously you need to do some sensitivity analysis to see the impact of the inputs on the outputs. And at the end of the day, as I was going to say, that essentially you need to improve the process, and you need to identify the hot spots where they're coming from, whether it is CO2 emission or PM10 or any other emissions indicators, where they're coming from. You need to understand that. So we use various design and optimization softwares, flow sheeting software. I sort of probably am custodian of a list of softwares, probably worth would be $200,000. So that SysCAD, MetSim, HSC developed by Autotech, as you know, flow sheeting softwares essentially I'm talking about, even Aspen. And then using those sort of softwares, you generate flow sheets, and then you have got lots of other costing databases you can use, and say Aspen Economic Analyzer, or you can use online sources or even the supplier's code, and then you can do that costing exercise. And also we have a lot of subscription to cost estimation handbook. We have our own in-house database and T-eval softwares, but also lifecycle assessment software. These are the two most popular ones, CIMA Pro and Gabi, and both we have got access to and license. We have to use it to use this. And also the databases like EcoInvent database and other Australian databases. And as I said, our own in-house experiences. So I think I'm with that sort of broad briefing, I'm going to talk about what is life cycle assessment. So I'll give a bit of background, and then at the end of the day, can you please mute everyone except myself? So life cycle assessment, as I said, I'm going to talk about. Sorry, I think somebody muted me too, so I've unmuted myself. So anyway, so that as I said, I'm going to talk about life cycle assessment, but introduction to life cycle assessment, but at the same time, what's the application in iron and steel industry, which we have done extensively. So when I say life cycle assessment or any environmental indicator or sustainability indicator, people often talk about our technology is sustainable. If someone is going to sell a technology to you, I suggest you ask these questions. What is the ECWW footprint? At least there are other indicators, but these are the 4 key indicators where we coined this term ECWW, and I sort of tried to popularize within the industry circle. And what is ECWW stands for? What is primary energy? So E for energy, C for carbon, W for water, and W for waste. So that's why I say ECWW footprint. So what is the primary energy footprint per ton of steel? What is the carbon footprint per ton of steel? What is the water footprint per ton of steel? And so on, waste footprint per ton of steel. If they are low, then you can say that product is green. If the technology can generate product with that sort of low footprint, you can say that's a sustainable technology. That's my definition. And also you can look at other indicators, but at the end of the day, those 4, I think the key ones, and you can measure very nicely. So when you talk about life cycle assessment, these are the concepts we are talking about, that resources, extraction and processing, production, distribution and use, and disposal and recycling. And everything, as you can see, raw material inputs, water use, fuel, energy use, these are the inputs. So these are the inputs we are putting to make some raw materials to a product through processing. And that's the chain we are talking about, A to Z, I call it sometimes. And obviously they will have outputs, so resource depletion, air pollution, heavy metals, toxic chemicals, greenhouse gases. We are talking about carbon footprints all the time, which is a quite popular term nowadays. But what about waste footprint? And also at the end of the day, what sort of impact they're making and where they're making: ecosystem degradation, acidification, eutrophication, ozone depletion, climate change, water scarcity and biodiversity loss. Those sort of things are happening. So we are talking about what are the inputs. We are accounting along the value chain, and also we are trying to see what is the impact, in what way that is affecting on our environment. And as you can see, if we define environment, it's all everything around us, isn't it? So again, when I say what is ECWW, here essentially ECWW plus maybe other environmental impacts, you need to look at that. And good thing is that we are all engineers and we know what are the units, we need to measure it. So when you talk about energy, embodied energy, so megajoule or gigajoule per ton of steel, carbon footprint, kilogram equivalent CO2 per ton of steel. So that's what is the measurement for carbon footprint or greenhouse gas emission, or GHG, or global warming potential. There are different names, but at the end of the day, you need some input units, and that's the unit. What is the water footprint? Kiloliter or megaliter of water per ton of steel, and then same way waste footprint. So, and then what has to be, you need to be, these numbers need to be close to theoretical, practically minimum. It's not possible sometimes, close to theoretical, thermodynamically not possible. So you need to be reach practically minimum, and then you can say minimum through best combination of technology. That's what I'm saying. What's the reduction opportunities or strategies you are employing? And obviously that water footprint, that has to be minimum with as much as recycling as possible and reuse of water as possible. Waste should be as minimum as possible. So those, if that is the case, then you can claim that your product is green, or you can claim that product is sustainable. So I'm just not going to too much about LCA, but I gave a bit of introduction how that works, as you can sort of have some flavor. But at the end of the day, there is a number of standards nowadays. International Standard Organization, ISO 14044 2006. That's one of the standard was developed for a while ago, and that's probably currently being used. So if you want to work as a consultant in this space, or if you want to employ a consultant in this space, you probably need to be familiar yourself with this standard. So ideally, the LCA has got 4 stages or components. One is they call it goal and scope definition, inventory analysis, impact assessment, and then interpretation. So goal and scope definition is generally say why you are doing this LCA and for whom. Who are the stakeholders? Is it the steel mill or is the other people? And if it is a steel company, who else they want to involve, kind of that. Then the next one, very important, is the boundary demarcation. Are you talking about cradle to cradle or cradle to gate or gate to gate? Some organizations, they think that they don't know what's happening outside their organization. So within the fence, for example, a steel mill, what is happening within the mill, what is coming in, what is going out, and that's your boundary. Then you can say gate to gate. So, and then you have to collect data. You need to see what impact category you are going to select. I mean, as I said, ECWW, and there are many other impact categories or impact you can select, impact indicator, I would say. And then you need to assess their interpret and the sensitivity of the inputs also. And at the end of the day, you need to update it continuously, so that because the technology is changing, the data is changing, so you need to have some sort of mechanism so to update that. But at the end of the day, what's the purpose of that is improving. So you need to understand what are the hotspots. So again, if we diagrammatically, if we express that, so we have what we call environmental interventions, raw material extraction, emissions that's going to the air, water, or soil, physical modification. We are changing the land potentially if we use land for any particular product or process, noise, for example. And we call it in LCA 2 kind of indicators. One is called midpoint indicators, and another is called endpoint indicators, which related with the damage. Impact indicators make some damage. And then if we categorize, first talk about damage, then either human health or resource depletion or ecosystem quality. These are the 3 broad areas we are having an impact. But if we want to have, these indicators have got units, but essentially these are the indicator list depending on where you are located are important. So climate change, resource depletion, land use, for example, climate change is greenhouse gas emission. You need to express that in terms of unit kilogram of CO2 equivalent, for example, per unit of product, and so on and so forth. So that these are the basically ECWW will be fall here somewhere. So then again, if I say that global warming potential, which is carbon footprint or greenhouse gas emission, that's kilogram CO2 equivalent, actually should put an E. Photochemical oxidation, eutrophication, carcinogen, toxicity, each has got units. You can see that water use, kiloliter of water. And I was categorizing under 3 main category, human health, ecosystem damage, and resource depletion. And you can have all these, what is called within the human health category, disability adjusted life years or DALY unit. Now, I'm not going into too much of detail of LCA today. So what I need to see, I need to go through that, because life cycle assessment requires a lot of data. It's a data intensive process. But now good thing is that the work have started in Europe. There are now softwares, they have packaged the data into a database, and they have, I'm sorry, those who are familiar with all these LCA concepts, but these are those people who do not know much about LCA. That's I'm sort of saying that still sort of in the early part of LCA, you need lots of different industry sectors. In Australia, for example, we call it AUS LCI, Australian Life Cycle Initiative, database initiative. So essentially that each country have their own data sets, because processes and distances and things like that, they vary based on the geographical locations. Maybe the energy grid has got different carbon footprints. You need to understand that. So when you say energy, electricity, for example, it can come from hydro, gas, coal, wind, and a lot of other sources, solar, etc. Same with manufacturing, and all these industries are very much interlinked. And you can see that probably that building industry, for example, timber, iron, metal is here. So we used to call BPIC. So we had a good data sets in Australia under this scheme. So any life cycle assessment have good database and data sets around this area. Another concept is called scope 1, scope 2, or scope 3 emissions. So essentially, when I said cradle to cradle, that could be a scope 1, scope 2, scope 3 all. So scope 1 is generally within the fence, what is happening within a steel plant, for example. Whereas that's scope 1. Scope 2, if you purchase electricity from outside or heat, that's scope 2. If you have your own, that's within scope 1. For example, captive power plant, that should be treated within scope 1. But if it is you are taking electricity from the grid, national grid, that should be treated within scope 2. Any other things, for example, your employees are traveling, your employees are staying somewhere in the hotel, everything else, your downstream supplier, that is scope 3. So often calculating scope 3 is quite difficult because that's very broad. But some organization, maybe that is relevant. But manufacturing plants or manufacturing industries like a steel plant, generally scope 1 and scope 2 is most relevant, and you need to focus on that. And environmental product declaration, another thing, another sort of development in particularly in Europe and other countries, but it is mostly still sort of I would say optional stage. But for example, if you go to a supermarket, you want to buy cereal, it has got packets and it has got all these the food values, energy, fat, sugar, this and that. This is environmental product declaration is kind of that. For example, when you sell your steel, it have a it will show that footprint of ECWW or any other indicator you mention. And if you do that, you need to have that should be LCA based. So in Australia, another thing what was developed is called the Steel Stewardship Forum and called Responsible Steel. And you can see that the diagram is like the life cycle assessment concept. Mining, because everything starts with mining. You need iron ore, and that starts with mining. And Australia probably produces 800 million ton a year. Probably you can see that large production comes from Australia and Brazil and China. And also I know India is a big producer too. But if you talk about export, Australia is one of the largest exporter of iron ore. Iron and steel industry, steel making, and then product manufacturing, use, and recycling. So all these you need to look at. And a steel chain footprint project, I think CSR was involved. We had in Australia, BHP, Rio, they are the iron ore manufacturer, iron ore miner. We have got FMG and few other couple of players, but mainly BHP, Rio, and FMG or Fortescue Group, Fortescue Metal Groups Limited. They are the iron ore miner. And then we have got two steel maker, BlueScope Steel. One is still under Liberty Group, and now under Sanjeev Gupta, Liberty in Whyalla. So we have got two blast furnaces operating currently in Australia. We had three. One was shut down, and you know that we together tried to develop this for a steel certification program. So I think this slide is everyone you are familiar with, particularly you living in Durgapur. It's not unknown to you. So iron ore, coal, we put them together. If it is iron ore is lump, that okay. If it is not, it is fine. So you need to sinter it essentially. You need to some form of agglomeration and then put in a blast furnace. We get essentially hot metal and slag, and then we also need to slag limestone for slag making and crushing and going there as a sort of in the system. And then you get that molten iron goes to a BOS furnace and you make steel. So end of the day, you need to understand, and sometimes you can use the gas as a fuel, but etc. But this whole, obviously you are very close to the steel plant. I know it's a quite complex manufacturing process, and we need to go step by step to understand where the CO2 emission coming from, what are the best way to reduce that. Yeah, I was going to say limestone is a sort of fluxing agent, and any other things you can, and not only that, after steel making, you can have stainless steel, you can have other alloys and etc. But broadly, integrated steel plant is like that, as you know. So I think I'm going to talk essentially, probably by this time you have got some flavor. We don't have a lot of time, so I'm sort of constrained by time. That life cycle assessment, I've given a bit of introduction so far, what it is, what are the database. We have got number of softwares, but we have used that for iron and steel making. And first thing is we need to do iron ore, and that's there is a book called Iron Ore Mineralogy, Processing and Environmental Sustainability, published by Woodhead Publishing. I think we are going to revise that, and for that work we had a book chapter here, and I'm going to revise that chapter. That will be a new edition anyway. And also I'm going to talk about development of low emission integrated steel making process. Dr. Sharif Jahan Shahi, who was a metallurgist, led that project over many years in CSRO, at least 12 years, in collaboration with Blue Scope Steel and One Steel, and I was one of the key member in that group. And I think Journal of Sustainable Metallurgy, if you look at that, was the first paper, and it is quite long paper we published in that one. So mainly I'm covering materials from here, but with from other publications too. So as I said, I am not going to talk about iron ore processing or inside the iron ore mining. So, but in Australia, what we do, you need to drill it, blast it, load it, and hauling, obviously crushing, screening, stacking, reclaiming, rail transport, port operation, and that goes to deliver to a port. Say most of our iron ore operations in Western Australia, say probably 400 kilometer north of Perth or north west, I would say, or northeast, and then port headlands. So there are several ports. Karatha, they supply iron ore through shipping. And in this case, I've said that 1 ton of iron ore, if you produce 12 kilogram of CO2, and that is delivered to the port. Now you have to add shipping if it is going to Japan, or if you're going to Korea, or China is our main customer, majority at the moment. And we actually shipping is, that bar will be quite high because shipping has got a large contribution. So I'm not considering here. So, but anyway, iron ore mining, as you can see, per ton of iron ore is not a big CO2 producer, but we produce 800 million ton. It's a huge number. So we're looking at options that instead of iron ore, can we do something, say maybe dry it, maybe agglomerate it, maybe beneficiate and agglomerate, and maybe make sinter, and then or pre-reduced iron, and then ship it. And does that impact in terms of CO2 emission advantage, things like that. So that's what's going on, and I can give you the references. You can download that and look at that paper, how we have used LCA to calculate the impact of iron ore 1 ton. And then obviously iron ore, as you can see that, as I said, it's not a lot. More you go downstairs of steel making, program sintering, you add CO2 increase emission. This is, I'm talking about GWP, or global warming potential, in kilogram of CO2 equivalent unit. So almost not a lot, 0.3 maybe kilogram of CO2 per ton of steel. And blast furnace iron ore production, that is about 1.5 ton, 5 kilogram of CO2 per kilogram of steel, or ton of CO2. So if you look at this unit, it's either you can say ton of CO2 per ton of steel, or kilogram of CO2 per kilogram of steel. That's the same thing. So we're talking about blast furnace 1.5. That's the largest component, because you, as you know, you are all metallurgists, that coke or coal or carbon material is used to reduce iron, and also the energy. That's the mainly CO2 emission coming from there. And then you can see basic oxygen furnace and casting, and you can add all of them, you can add up, it probably will be close to 2. And there is another slide I have got to compare between sites and things like that. Probably we can discuss a bit. So now we know that, okay, roughly 2 ton of CO2 in this particular case. Where they're coming from, we know. So what's the best way to reduce that CO2 emission? What are the strategies? Various countries are working on various ways, particularly I think Japan, Korea, POSCO, European, they did ALCOS, ultra low CO2 steel making. I think Koreans did oxygen steel making. Japanese also, they tried to use hydrogen and other options. Brazilians, they did a lot of charcoal based steel making, so using eucalyptus plantation, making into char. So we looked at in Australia, we looked at that, and we thought maybe in Australia we have, because our forest industry is very big and we have got a lot of biomass and land, potentially we can use biomass application to steel making. So that was one of our ways, we thought. So as I said, 2.2 maybe ton of steel and CO2. And that CO2, I mean, we can see that that sort of cycle I'm talking about. So you know that at the end of the day, sun is the source of energy. And if you grow trees, there will be, definition of trees to me is that CO2 plus water, I mean, because that water is extracted from the soil by the trees in the presence of sunlight, and that's sugar, or that's charcoal, or that's carbon, and that's carbon material we're trying to use here. So you make carbon and then put in a steel plant, and you obviously, when you have that one, you grow CO2, and maybe we grow back, basically suck that CO2 from the atmosphere. Maybe we cannot do that exactly, but at least some amount. Then we can recycle back that wood made into charcoal. So at least some sort of closed loop system using biomass. So that was one of our objective, and we have done a lot of modification, and we thought maybe 50% of CO2 you can reduce in that ways potentially. If you make charcoal from sustainably managed forest or plantation, some kind of sustainable biomass or biocarbon you need to make. And based on that, we developed a pyrolysis process and pyrolysis plant. And it is about, if you run it continuously, it was 1,000 ton per year. And we tested a lot of processes. One is still used our charcoal to put in their furnace to make some test work, and all was found okay. But at the end of the day, we need to compare the cost of charcoal with the coke, and currently coke price goes up and down, and that was at the end of the day. We were doing some activities around that, sponsored by steel industry. So as I said, using life cycle assessment technique, so gross total 2.17 ton of CO2 you can see, and where they're coming from: off-site electricity production, mining and processing, sintering, coke making, blast furnace, bay of furnace, that exactly I have shown you in the previous slides. And now with charcoal, that can be reduced. If we use charcoal without any byproduct credit, then it would be net 1.4 ton of CO2 per ton of steel, potentially possible. If you charcoal with other byproduct, for example, when you make solid char, you made probably some liquid fuel, and if you can take that into account, you can potentially reduce to 0.96 ton of CO2 per ton of steel, or almost more than half. So that sort of evaluation we have done. And actually, charcoal metallurgy was not new. It's a ancient process. And actually, I went to Delhi just to see Qutub Minar, and you can see that pillar, iron pillar in Qutub Minar complex, was apparently made by charcoal. Also, we did another one, that what we call dry slag granulation process, or slag dry granulation process. So essentially, when you have got a steel plant, you are making slag. You are obviously, you know those, and it is coming at 1500 degrees Celsius. And we said, okay, can we extract heat from here and also reduce the water content, water consumption during slag? It is a dry process, so you don't need to reduce water. So at the moment, that technology is quite advanced stage, have been licensed to a company in China, and hopefully if they can make they can demonstrate at a large pilot scale, that will be around the world. And so that's what is showing. So we have got a small rig, and we have got a bigger rig also now, I think bigger size, and in China they have made a even larger one. So I hope that, I'm not sure whether that is, yep. So you can, I'm not sure the video is going, but that's basically drops of slag is dropping on a disc, and that is moving around, and that's making nice granules, and that can be potentially used for cement or other materials. But good thing is that the uniformity of the process, and also you can extract heat. These are the two areas we looked at, and you can see the granulated slags compared with water granulated. And in terms of color, they're different, but essentially they are the same, more or less similar applications. So in our case, what we did, I'm conscious of time, that this is our concept, that you have got biomass, you use energy, or basically you charcoal and liquid fuel potentially you can generate, use that in iron and steel making, and also you granulate slag, and together you make kind of more sustainable process. So in Australia, we had also a lot of problem with soil salinity, in particularly Western Australia. We have a lot of big farms, big land area, And one of the ways to reduce salinity is to planting trees. So we thought, okay, large area, let's plant trees and then make large scale, large amount of biocarbon so that we can make this process more sustainable. And as I said, that the Jahan Shah et al., you can look at that paper. So just to, this is the, I think one particular year, one of our student did and will also work together, PhD student, that we collected crude steel production in 2013. I think this is probably ArcelorMittal, but there are lots of different companies. This end is more electric arc furnace. So that's why production is around 0.5 ton of CO2 per ton or 0.5 kilogram of CO2 per kilogram of crude steel. That's based on we have not done LCA. It's mainly compiling the number the companies have reported. So I think the large is between 2 to 2.5, as you said, that way 2.2. There are some plants that are doing very well. Although these, as I said, towards this end they are not integrated steel plant. They are more electric arc furnace. But here you can see that interestingly, that some of the plants are even producing 3.6 probably ton of CO2 per ton of steel. And I don't want to name them, but I know they are from India. So some of these areas, I don't know what's the reason. I wish we could look at more detail, but obviously I think there are some good steel plants here from India, but I don't want to give the names. But essentially, these are all sorts of steel plants, and some of the loops at. So at the end of the day, we would like to see what would be the average, as I said, that close to theoretical. Not necessarily you cannot have theoretical, but as practically minimum as possible.
Achha, Dr. Huck, I am interrupting. Dr. Huck.
Can you hear me?
You can use the laser pointer, because your pointer is not
showing,
and it is not showing clearly because the background is white. Therefore, you can use the laser
know how to use that one.
Yes, just at the bottom, you can select different types of laser are there.
Is that one? No, that's not the one. Sorry. Maybe that's the one. Laser pointer. Yes, I can see that one. So that's right. That's the one. So here you can. What I was saying, that some plants are producing 3.6 maybe ton of CO2 per ton of steel. Some plants are making, forget about those electric arc furnaces, but even these are probably around that range. They should be around 2.5. So if a plant is producing that high, maybe there are some reasons. Obviously, there are technology, there are raw materials and everything else. But and exactly that's we have done for other metals. I mean, where is the mine? What are the grade? What are the technologies? And slowly, what we'd like to do, we cancel all the variables which can contribute. Then at the end of the analysis, you will find one reason, the differences between the sites or between the plants. And that would be very interesting exercise for any steel maker, that to see that where they are and why they are above. If they're below of the benchmark, that would be fantastic because you are doing really well and more than well probably. But if you are above that, and how much above that, why you are above that number and how to reduce that. That's probably my take from that slide. So then I would like to go in the next slide. Sorry. So now I'd like to introduce the new ways, a lot of discussion happening. I know that Dr. Mondal told me to focus on this hydrogen steel making, or even oxygen probably, because when you make hydrogen, you make oxygen. So, but I have, to be honest, not a lot of experience, no experience to be honest, but we are working on hydrogen industry because in Australia, we produce a lot of metallurgical grade coal. And I know that India imports and our 2/3 world's market, we sort of supply met coke or met coal. And India is one of the largest importer of Australian metallurgical grade coal. So, and also currently also metallurgical grade coal, iron ore and thermal coal. And on top of that, recently last particularly few years, last year we had $50 billion worth of LNG industry, liquid natural gas. Now our objective, because these are all fossil fuel we are exporting, including uranium, we export a lot also. We are trying to develop a new industry based on renewable, and that's hydrogen. In the 20 years down time, if we can see hydrogen becomes like a $50 billion industry in Australia, like LNG, we have a mission in CSRO, and not only in CSRO, Australia probably where government has invested a lot of money, at least about a couple of thousand or maybe 2,000 researchers are working. At least in CSRO, I can say at least couple of hundred researchers are working in hydrogen space, and I'm leading one of the chunk of the work. So they are talking about electricity, and in this case, electricity is renewable. In Australia, we have got large solar and wind project. Cost is, well, hydrogen came before and came and go, but now the discussion is quite interesting because the electricity price has gone down significantly, particularly renewable electricity. And that makes this discussion really interesting because hydrogen, to make hydrogen, you need a lot of electricity. So if you have hydrogen, then you can put, or basically the electricity, you can put in an electrolyzer, you can split water, make hydrogen, you can directly reduce iron. And there is a paper, Da Costa, I think that Journal of Cleaner Production, that paper has got a lot of interesting information. And I think one of the number, it is quoted that around 80% of CO2 potentially can be reduced using hydrogen. But again, you need to look at where that hydrogen is coming from. I think 33% replacement of carbon with hydrogen would result in doubling of production cost, but significant reduction of CO2 emission possible. But obviously, these are the more assessment required. There are a lot of discussion, as I said, and Professor Mondal said that there are a lot of interest in India too. But my objective is that you need to make a lot of hydrogen. And unless you make a lot of hydrogen, this discussion is futile, really. So how do we do that one? I think I need to go back to that next slide. So these are the flow sheets. If you look at that kind of flow sheets that we have, that's basically, I'm spending a lot of time with two of my PhD students and colleagues that the flow sheet, techno-economic and life cycle assessment of this kind of flow sheet. So to make hydrogen, you need a lot of water. And in Australia, we have got coastal sites. So we have got sea around, a lot of water, seawater. And we can, a lot of countries can have access to that seawater. You can desalinate it using renewable energy and then put in an electrolyzer. A lot of companies now producing Siemens, ThyssenKrupp, hydrogenics. And so solar and wind energy becoming cheaper, popular. They can go even desalination. They can go to the electrolyzer. You split water, you get hydrogen, and then problem is that in Australia, we have a lot of land. We can produce a lot of solar energy, wind energy in the coast. If you put them together, the capacity factor can go up, even probably up to 70, 80%. But thing is that you make electricity. What do you do with that? Our electricity need is in the cities, and we have got how do we export that? That's the challenge. So that's why we thought maybe let's make hydrogen. And again, hydrogen transport is not easy. So we thought maybe make ammonia using air from the nitrogen from the air, put them in a reactor, make ammonia, then export ammonia in the liquid form to another country like say, Japan or Korea, because ammonia industry is already established industry. A lot of ammonia has been transported by shipping and other things. And that liquid ammonia can be broken back to hydrogen, and we have got technology for that. That's one of the there was one of the barrier until CSR has resolved this, and we can in that cracker we can make pure hydrogen, and that pure hydrogen can be used either in industry or transport or anything else, or even steel industry, for example. And ammonia also can be used for currently hydrogen industry. Essentially, there are 50 million, 60 million tons of hydrogen is used or produced per year. That's mainly in the fertilizer industry to make ammonia. So already that's established that's an established industry. Refrigerant or other use potentially possible. But our objective is to improve the mobility and maybe industrial use, and potentially steel making would be the first choice probably. But we have not looked at that detail as yet. You can ask me any question about relatively. I have some experience, but still we are learning. At the same time, it's a very challenging task to make this industry a commercial in this next 10, 20 years. If we can make it some inroads, that would be fantastic in the world globally, because many countries are working around that. I know the North Americans have done a lot of work. Europe is happening. Even Middle East, they're talking about large hydrogen projects in Saudi Arabia or Morocco, places like that. But at the end of the day, these electrolyzers and these, if you export hydrogen, obviously exporting hydrogen, the shipping is not well established as yet. We are working with the Japanese companies in that area. So basically, what I was going to say to you that hydrogen is still making, but you need to make hydrogen fast, commercially and economically, and then we can look at that. There was a lot of news I saw that hydrogen steel making in Europe, Ovako, a company, a Swedish company. But if you look at that, Ovako first in the world to heat, that heat, a lot of people exclude, they say that, oh, first hydrogen is still making in Europe, but actually they're together with Lind gas, Ovako has concluded a full-scale trial using hydrogen to heat steel before rolling. And they're saying the historic development for the steel industry proves that carbon dioxide emissions from rolling can be eliminated provided that right financial support and infrastructure are in place. But again, it's a rolling mill in Sweden, Hofors rolling mill. So it's not necessarily steel making in the rolling, in the hardcore steel making area, but that's the one of the claim I found. So I think I have covered mostly these sort of areas: sustainability, life cycle assessment, application of LCA, in this case steel and iron making, iron ore, iron making, steel making. And one of my senior colleague, Dr. John Rankin, he is one of the best metallurgists I have come across, and he has got a minerals, metals, and sustainability meeting future material needs. And also we probably published metal sustainability, another book. So some of the resources I've spoken, you can find in this textbook quite well. So the key messages I said: process evaluation assists with decision making, process and plant design. Life cycle assessment is a recognized objective tool for environmental evaluation of process or product with international standards. Metals have different specific carbon footprint depending on ore grade and technology, and that applies also with steel. Specific carbon footprint is not the only story, but the overall total production of particular metal is important to know the global impact, and particularly steel. If you compare steel with aluminium or any other metal, steel is one of the lowest. 2 ton per ton is not a big number compared to say 24 ton or 40 ton, for example, magnesium, titanium, if you go to that sort of metal. But globally, 1.8 million, 8 billion ton, 1800 million ton of steel is produced, So if you multiply the 1800 by 2, it's a big number. So carbon footprint can be reduced with various measures such as renewable electricity, renewable biocarbon, and even potentially renewable hydrogen, which I just referred to towards the end. There are other environmental and social impacts need consideration. We all talk about carbon footprints, but obviously, as I said, ECWW, energy, water, energy, carbon, water, and waste, and also other footprints potentially. CSRO can evaluate process and projects for economic and sustainability metrics. This evaluation helps to identify hotspots, and we can recommend strategies to reduce cost and environmental impacts based on this evaluation. And that's what's the whole purpose of this. So if anyone wants to do an LCA work, and a lot of companies come to us, we have done in the last 15 years, a lot of them. And I want to ask these sort of questions. Or also, if you want to sponsor someone or you want to do yourself, you ask yourself those questions. What are the main objectives of any LCA study? How do you define boundary? You have to agree on the scope of this work. So that's goal and scope definition we talked in the beginning. Which life cycle indicators are to be reported? Is it just only the carbon footprint, or ECWW, or on top of that energy, carbon, water, waste, or other footprints also? How much input data are already available? How much data you need to collect? You need to estimate the resources to undertake this work, and then you need to develop a team, you need to collect data, you need to develop LCA model and generate results. And what do they mean? That's interpretation of results and another aspect. Is an external peer review required? According to standard, if you want to have a validated credible LCA, you need to review it by another external peer. how detailed report is required, and will it be released for use in public? So these are the questions you need to answer before you embark on an LCA study. So I think I have covered quite a bit, and I have taken, probably I'm not sure about the time, but hope that gives you quite understanding
10
of
minutes.
when you
You have 10 to 15 minutes more.
so when we talk about sustainability, so we talk about obviously, as I think one of the speakers said, it's a bit of vague and it's used in different context, and some people use differently. But I think we are all engineers. We need to understand the numbers in terms of metrics. And my dream is to make metals which have no emissions. But obviously that's not possible, as I said. But as minimum as possible, theoretical, if not possible, minimum ECWW. And that obviously, because we need to look after the environment and we need to keep the economy going. And again, the 3 E messages: energy, environment, and economy. So we sometimes also introduce triple bottom line: social, environmental, and economic. So, but LCA is a nice tool, and obviously it has to be global effort to make steel, and it's a global industry. And to, I mean, at the end of the day, we have, as a producer or user, we have responsibility towards the environment. After all, there is one earth. We need to care and share. So with this message, I think I'd like to finish, but I'm happy to have some questions and discussion. Thank you, Dr. Mondal. So probably I will stop sharing screen here. Is that okay?
Yes.
No, sir, you be on your screen. Actually, the questionnaire will start, and I will request coordinator of this event, Dr. Shatadal Ghorai sir, to please come up and start the questionnaire session.
So by the way, also my details are there. If anybody wants to connect with me, my email, and you can find me in LinkedIn. I'm happy to help if anyone needs some assistant in this area.
Thank you, sir. Sir, it was a very elaborate talk in this very short time, and thank you so much for giving the talk. And the questionnaire will just now start, so please have a bit patient.
So,
Arup sir, I would request you to please
Yes,
start
all
with.
participants are requested who can who want to ask question, just go to the raise your hand option. Fifth option, which is available, one hand uh, picture is available, raise your hand option. You can click the raise your hand option and ask your question.
So just also in the meantime, I'd like to say that in Australia, as you know, we are lucky country. I mean, any metals you talk about, we are probably top 5. Some of them are top 3 or even top number 1. So we produce a lot of iron ore. Unfortunately, our steel industry is very, we call it two-speed economy. Essentially, mining is very strong. So we essentially dig and ship kind of approach. So we mine iron ore. If the question comes, Dr. Mondal, let me know. I'll stop. But in the meantime, I'm sort of giving some information on that. So 800 million ton of iron ore, roughly, I mean, plus minus, I'm not giving the exact number probably. We export, produce and export. We only process ourselves maybe 8 million ton. So you can see that very small percentage, because we have got a steel mill in near Sydney, a city called Wollongong. One is blue scope steel that we had 2 blast furnaces. One we had to shut down. I think one is still running, and then one in
Yes,
close to
first
Adelaide.
question, I am
All
interrupting.
right, so I'll leave.
First
Let Dr.
question from Jyotirmoy Chatterjee. Unmute yourself and ask the question. Jyotirmoy Chatterjee, unmute yourself and ask your question. Jyotirmoy Chatterjee, unmute yourself and ask question. Yes.
You can hear me now?
Yeah.
Yes, I can hear.
So my question is to Professor Huck, and the thing is that when you are using all those other uh, efficient technologies, then the procurement time will not increase, or the thing is that the total time span for from the inbound inventories and from inbound logistics to outbound logistics part, the whole time span will increase. That is the main problem with that.
So what's your question? Is that you are saying that new technology introduction is difficult, or what's the question?
So my question is that how to implement the new technology and making it economically viable for the total lifespan of the thing, because total supply chain part.
Okay, so I think I can comment on that. I'm not sure I can answer exactly, but thing is that my approach would be that if you want to introduce a new technology, completely new technology, obviously you need to have capital investment, but maybe some retrofitting. For example, if you introduce a biocarbon or charcoal, obviously there are a lot of challenges because charcoal is very light compared to coal and coke. But maybe even charcoal we can look at to make it more densified charcoal, potentially that could be equivalent to coal and coke, and then so that you don't need to, maybe do not need to modify too much of the existing system, but obviously you need to have supply of that new raw material that could reduce CO2. For slag granulation, obviously you are currently probably have some system. Obviously you need, if it is a completely new technology, you need to make some investment on that capital front, that side. Same with hydrogen. But I understand in DRI in India quite popular. You are using natural gas to make steel, or maybe gas from coal and use in the system to make DRI. Some sort of if you have iron ore, your iron ore I know not very good quality. Maybe some sort of beneficiation, upgrading, pre-processing. These sort of ways, I guess that potentially can reduce CO2 emission if that is the main objective, and other environmental impact. So that, I don't know whether that answers your question, but that's my comment.
In this connection, I want to add something.
Yep.
In India also, some initiatives are taking. One is using of this highest coal for coal gasification, followed by the DRI route to make the steel. One initiative we are taking also. Acha, one question came in the chat box. Amit Kumar Singh, he is asking, what are the future? Acha,
Sorry, can
I request
everyone mute? Yeah,
mute.
sorry.
Yes.
Yeah, go on. I didn't understand it. Dr. Mondal, can you repeat the question?
Yeah. Question is, what are the future industrial prospects for biomass charcoal? To be more specific, you can talk about the following points. Yield of charcoal is very low. Land required for plantation, and obviously cost of biomass charcoal, as we are talking industrial feasibility.
Thanks for that question. Actually, we looked at a lot in Australia. So what happened in Australia, situation different, and I think that will differ between countries. If land is precious, obviously, because for making charcoal, we looked at that, for example, Australian capacity, we have got enough biomass. But if it is, the demand is very high, then we need to look at. But another thing is that not only biomass just from wood, but there are a lot of waste biomass potentially is being used somewhere at a low value or low, I would say, low utilization point of view. So if it can be taken, nowadays pyrolysis process has improved a lot. Previously, which we used to say, the blacksmith used to make charcoal, and some countries very low quality, low sort of crude technology. But a lot of countries, a lot of companies, at least Largi and others, have developed charcoal plant, which is relatively, I would say, sophisticated, that can produce multiple product, and potentially it can be commercially used. But I wouldn't say 100% charcoal is very easy, because although Brazilians are doing it, but their charcoal, their blast furnaces are smaller, and they have got already existing dedicated plantation. ArcelorMittal, for example, they have got for making charcoal. So it is commercially possible. It's not possible that's not the case. But say countries like India, or where there are not a lot of land, can it commercially be done? I would say probably not 100% replacement. You think about maybe 30% replacement, and is that potentially possible? Probably immediately, without too much changing of the technology, possible. That's my feeling.
And also, charcoal is not the newer one. Charcoal is older one. Charcoal technology is older. One question came from our social media platform, from Facebook Live. Chiranjeevi Kanari, he asked that is it safer to use ammonia in public? If so, what the conditions and storage devices? Please explain, sir.
Okay, thank you. So there are a lot of discussion about ammonia and also hydrogen. So in this case, if we apply, I mean, there are thinking about using ammonia in direct engine and generate power and things like that, if we talk about that. But for steel application, I would say probably more hydrogen. You need to, in Australian situation, what we are trying to do, we are trying to make our renewable energy is very cheap because we have got a lot of land, Central Australia, for example, around the coast. So solar, wind, we have got a lot of energy, electricity. Now we cannot export it. But if we make hydrogen using seawater, for example, it's difficult to export because we need a special vessel for hydrogen. There are not many. But in the ammonia area, it is established technology. Ammonia is transported around the world in ships, in countries. If anyone has got a fertilizer plant, and in particularly in South Asia, we know that our agriculture is the main product. Agriculture is dependent on fertilizer. So we make a lot of fertilizer. So ammonia storage, ammonia use, there are some concern about leaking and things like that, but it is a smelly gas. So you can easily recognize. So my area is not in the health and safety area. I'm more looking at the production side, looking at the CO2 emission, techno-economics of production, and same with my steel experience, where the emission is coming from. So I cannot comment on the use potentially, but what I know about the ammonia industry is relatively safe, and they have got a lot of safeguards, and they're using very nicely. And there are a lot of, I would say, bad news about ammonia or even hydrogen. Is that answer your question?
Dr. Rock,
yes.
There is a question from Abhishek Kumar. There are two questions actually. And how can we minimize CO evolution social media?
Actually,
I cannot
your
see
sound is
very
not
good.
clear. I
So
am repeating.
Okay.
Your sound is not clear. Actually, from our social media platform, YouTube Live. From YouTube Live, Abhishek Kumar is asking two questions. One is what is green steel and green steel making, and number two is how can we minimize the CO2 evolution in blast furnace?
Okay, so I will go to the first one. I think the whole talk I tried to explain, when you claim a product is green, what is the credentials of that? And one credential is that ECWW footprint and other indicators. So that should be close to theoretical. So or as minimum as possible. So I think 2 ton of CO2 per ton of steel, probably conventional process. If you want to claim green steel, you need to go probably further below. That's one way to determine whether you qualify for green steel. So again, that benchmarking, if your industry or your producer or you are a producer yourself, you need to look at that. Are you below that benchmark, current sort of fossil based system, if you compare with? That's you can define that green steel, but you need to have that product declaration, EPD, environmental product declaration, which will require LCA of your process, and you come up with number and define that according to that scheme. Now the second question is that evolution of CO2 from blast furnace. If you use a lot of carbon, you need to use it to reduce iron and also heat. I mean, you can have there are PCI, pulverized coal injection, there is direct coke. So there are various, in the sinter plant you are using carbon. So all these carbon, but in the blast furnace, all these raw materials together, and you are burning them or essentially heating them at 1400 degrees Celsius or something, you are generating carbon dioxide. There is no way to reduce that if you use carbon. So either use biocarbon, that's what we said in the charcoal potentially, so that you can reduce that way. Second way is that hydrogen or natural gas. Natural gas has low carbon footprint compared to uh, coal, coke. That's one way. Or maybe I think that some companies do that anyway. Use blast furnace gas, although they're very low value, low quality heat. You can reuse that and recycle that. And maybe the slag. Probably you can use that dry slag granulation. That's the indirect credit. And overall, although that is impacting your blast furnace process, not directly carbon evolution, but you can credit for that if you can use in another purpose, use of waste. So these are the probably the strategies you can use to reduce carbon footprint.
Use of blast furnace gas also through the upper stack region, it will also beneficial for decreasing the CO2 emission.
That's right. And when you dry slag granulation, you can recover heat at the same time, and you can make some steam, low grade heat although. Yeah.
Achha, next question from A.R. Dasgupta. He is actually retired executive director of ISCO steel plant. Sir Dasgupta sir, can you can ask question. Unmute yourself, Dasgupta sir.
Am I visible?
No sir. Make your video also on.
Yeah, I have made it on.
Yes, you are audible. You can ask.
Okay, so let me ask. So first of all, thank you, Dr. Mondal and
yes,
Dr.
yes,
Hawk.
you are visible now.
Thank you, Dr. Mondal and Dr. Hawk, Dr. Ghosh. Thank you very much for arranging such a fantastic program. And I am really thankful to the presentation given by Dr. Hawk. It was really a lot of things were new in his presentation. Now I have got two very specific questions. Question number one. Dr. Hawk mentioned about using hydrogen for the reduction. And as he was telling in the upstream, we need to put solar plants or maybe wind power plants for generation of the electricity. And obviously the land area will also be required. So considering all the capital investments, what will be the implication on the ultimate cost of steel if we go through that hydrogen route? That is question number one. And question number two, he was mentioning, Dr. Hawk was mentioning about the dry slag granulation process. As he knows that in India, mostly we are still doing a wet granulation process by giving forced water in dewatering drums, etc. So then after that, the granulated slag is used for steam and plants. So I would like to know, if we go for dry slag granulation, then how much sellable will be the product? These are my two questions. Thank you.
Thank you, Mr. Gupta. So essentially, with the obviously you need a lot of electricity to make hydrogen. That's 1 kilogram or 1 ton of hydrogen. 1 kilogram of hydrogen, you need 55 plus minus kilowatt hour of electricity. It's a lot of electricity, and that will, if that comes from renewable, carbon footprint is really low, obviously. So, but is that economically possible? I think countries like India, maybe there are a lot of solar resources, say Rajasthan or some desert areas, but you need to transport those electricity, obviously. That's another issue. High voltage DC cables nowadays people are using. There are long distances, high voltage DC cables are there, or offshore wind potentially. That's another option. But again, you need to look at that. In Australia, we are looking at the solar and wind farms. They're drastically per unit electricity. So kilowatt hour of electricity is very low compared to the conventional. So it's becoming down and down. And obviously, I can see in 10 years time, if this rapid pace of development going in the solar and wind technology or other renewable technology, you would get. Water area, another area, a lot of people question about water also, because not only electricity, you need water to split. So obviously you can desalinate it, and desalination takes also electricity, but it is not a lot in terms of cost. If you look at the pie chart of hydrogen production, desalination is a small part. But again, majority of our cities, what we are doing, we are using water a lot, and that's going to the wastewater. Particularly in countries like Australia, I know we have say Melbourne City, we use 150, I think 450 gigaliter of water every year. So that water is going through the people's houses and going back to the after treatment and going back to the system. So wastewater could be another source of hydrogen. So wastewater, renewable electricity, that would be good combination to make hydrogen. But again, if you're a steel maker, you need to look at what you are paying for your energy. Say your coal, or I know coal would be cheaper, coal compared to gas, for example, compared to hydrogen at the moment, say dollar or rupee per gigajoule. So if your rupee per gigajoule energy is comparable, obviously that time hydrogen will make inroads. And already hydrogen, because although it is taking a lot of energy, because the renewable energy become cheaper, we are thinking potentially this will be cheaper source of energy. So, but at the moment, I don't know. We need to look at that particularly condition in India, and you need to look at the resources in terms of electricity resources. So I cannot answer that question directly, but in Australia, we think in Australia, we are quite in a good position. The second one in relation to your question is slag granulation. So the benefit of slag dry granulation is that you don't use water, obviously. Second is you can recover heat, and the product you are making is quite uniform. You can control by controlling that disk speed and things like that, and your flow and so many things. But at the moment we are still that's more sort of near commercial, but there are few things need to be looked at. So I can tell you that that product we have tested, that's very similar to the existing system and maybe better sometimes, because in terms of uniformity. So I think those two areas, but again, I'm sort of not into the technology side of this area. I mean, deep technology side, rather than I'm more evaluating those technologies, because in CSRO we are developing, say, dry slag granulation is our own technologies. But anybody come to me, I do that techno-economic and life cycle assessment. So the same way I did for slag dry granulation and also hydrogen system we are doing now. So from that experience, I'm speaking. Is that answer your question, Mr. Gupta?
Yeah, thank you. Thank you, Dr. Hawk. Thank you very much.
So Dr. Mondal, you are in mute.
Yes, sorry. Next question is, what is major role used hydrogen in steel making?
Sorry, what's the question? What is the
major role used in hydrogen for steel making?
Yeah. So, okay. So let me answer one thing. So in Australia at the moment, not only Australia, why we are working on hydrogen? So the reason is that CO2 emission reduction, obviously. Now, if you look at where the CO2 emission is coming from, CO2 emission is mainly electricity. 1/3, if you globally, I'm not giving you the exact number, but roughly 1/3 electricity industry, 1/3 transport, 1/3 residential and other things. So now, if electricity, you can probably have, say, you can capture carbon and then, because it's a point source. But in the transport, say all these cars are using fossil fuel and generating CO2, you cannot put something at the end of it's difficult to collect because they are spread so much. So fast application for hydrogen would be targeted for mobility, essentially fuel cell car, hydrogen fuel cell car I'm talking about. Maybe you can make hydrogen gas. We are looking at even small systems, say solar PV in the home system. Can we take the whole home off grid? So you can make hydrogen gas, and then gas can be introduced in the pipeline, gas pipeline system. Say methane. With methane, you can introduce up to 10%. People claim that nothing, you don't need to change too much of the infrastructure, but above probably that you need to look at because hydrogen has got issues with the pipeline and transport system. So at the moment, people are looking at transport. That's the first one. Maybe then looking at home appliances, maybe hydrogen cooking and home cooking and things like that potentially, or electricity, obviously using a fuel cell. If you want to make steel, hydrogen as a heating and reductant, both, it can probably used as a carbon. You can replace 100% carbon with hydrogen. That is potentially possible, but maybe not now. Slowly you need to increase. But at the end of the day, that has to be economic, obviously, that the same amount of electricity or energy you are using making steel, can that be delivered with hydrogen? That's where the use will be.
Okay. Next question from Tata Steel Jamshedpur, Sayak Mohammad Basa. In next 5 years, what are the challenges to any steel industry? Second question is, in which direction steel sector should see, like digitalization, industry 4.0, etc.?
So I think what I can see, steel industry is quite in difficult situation. For example, electricity industry, they can move to nuclear, they can move to other, say CCS, even carbon capture and storage, although that can be applicable to steel probably, but they can go to renewable, they can have lots of options, fuel switching to reduce CO2 emission. But for steel at the moment you use carbon, you don't have much alternative. So I think from steel industry point of view, they need to look at all sorts of ways, maybe some sort of combined strategies where the CO2 is coming from. Obviously, we know that iron ore area, and maybe that also starting with iron ore. I mean, in Australia, if I give the example of Australia, this sort of things need to be thought globally also, that we produce iron ore in Australia, Brazil, India, China. They are the largest iron ore producer. We ship lot of iron ore around the places. So maybe we need to produce steel where the iron ore is. In our, if you look at Australia, we call it iron ore boomerang project. There was a discussion that in Western Australia, we have got iron ore. In Queensland, we have got coal. So we may have transport iron ore to Queensland, and we have got coal there. And we take coal to Western Australia. We have got iron ore there, so we make steel. So that way, you can reduce the contribution from the transport, that sort of thing. So a bit of consolidation or configuration, that's I'm giving an Australian example, but maybe within India, that same sort of things where the iron ore is being mined, where the coal is mined, can coal or carbon maybe replaced or reduced with other things, slag granulation, maybe biocarbon. All these things need to be, just one solution wouldn't fit all. So steel industry need to think around that. Then second thing, with the optimization, globalization, data analytics, industry 4, I don't have a lot of experience. I wouldn't say much about that, but I know that things becoming more smarter. So we know, like this sort of data collection from the industry, optimization. If you look at the steel making earlier, they used to use a lot of carbon, and that has reduced dramatically over the years. So obviously those data within the system will probably help to reduce that. So industry 4.0 will make some inroads because of that intelligent system, intelligent control, and optimized process, I would say.
Thank you. Next question from our student Doita Pal. She asked, when we use biomass from wood, given the imbalance in rate of cutting trees and afforestation, and also the difference in amount of carbon dioxide released on burning and the amount taken up by growing trees, how effective or in which time span can biomass prove effective to reduce CO2 emission?
Thanks. Nice question. With bioenergy, actually, I'm working for a while in this area. That always people say another 10 years, bioenergy, another 10 years, and never that 10 years came. So there are lots of issues. Obviously, I think one of the reason is the land, but I think with lot of new developments, particularly countries like tropical countries, India, Bangladesh, the growth rate is very high. I mean, South Asia, where there are a lot of rain, the growth rate is high. And there are also places where farmers, what we call social forestry, agroforestry, a lot of barren lands, hill lands, potentially that can be utilized under more. Actually, by the way, I started forestry originally and then came into engineering, so I have a bit of understanding how the forest department, because in Bangladesh one of my student is running the whole department. He's the chief conservator of forest, so we have sometimes discussion that what's the best way to handle this kind of thing. So there are opportunities. Obviously, fuel I mean, a country when they develop, they use electricity. Electricity is one of the form of energy. I mean, if you talk about the energy, I mean, that's another discussion. Thermal energy, electrical energy, fuel, biomass has a role, but because of land limitation, that always a bit of problem. But again, with the optimized system, as I said, that those barren lands, those fallow lands, a farmer can have some earnings, but that has to be planned in the areas. It is not suitable for every part of the country. Maybe some part of the country we need to use that, and that way we. But it's, I understand it's a probably general statement and question. I could not be more specific. Sorry to that student.
Nee, for your information, Daita, next speaker will discuss regarding the biomass energy as a reductant also. And next question, it come from Mr. Kiran Babu. As far as cost of CO2 emission is concerned, is hydrogen a better option than the conventional method? If not, will the mass implement of the technology reduces the cost as well as CO2 emission?
If I got this question, it's sort of economics related. So just to divert a little bit that, well, obviously I was talking about the steel industry is difficult situation because we are producing a lot of CO2. Now, one option could be that, I mean, at the moment, obviously hydrogen would not be economic. That's my feeling. Although it is because the electrolyzer and all these investment you need to keep in mind, and that is developing slowly. The electrolyzers and other equipment, capital equipment, a lot of industries coming in. Probably with time it will be. But another thing is that maybe carbon capture, not necessarily storage. So from a steel plant, we can capture carbon dioxide, I would say. Then like a power plant also, we can capture it, we can enrich it, so nearly pure carbon dioxide, and we can make renewable hydrogen, and we can react hydrogen and CO2 to make potentially methane or natural gas or some other carbon. So that way it would be, you need to look at economics, but obviously environmental benefits we would like to look at. We are talking about waste gas stream we are going to utilize, and obviously that has some benefit. One of the things we need to remember, I mean, one of my colleagues says that if we have some disease and say cancer, we go to the doctor and doctor say that this must cost the medicine. Do we care of the cost? So in this case, maybe immediately we need to care about the cost, but down the long term, if we want to really reduce CO2, we need to look at the technologies. Maybe that initially that technology will be expensive, but slowly it will make some impact. I mean, like in Australia, we had in 2012, we had almost nearly zero solar, not zero I would say, but not a big solar energy in residential home. Now it is $5-6 billion industry, and 3 million homes. In my home, I have got solar. Whole year I don't need to pay any electricity bill at all. So I used to pay $1,200 a year. So these things suddenly came, and I invested probably $3,000, $3,600 with a bit of subsidy, and I got it back in, probably I'll get it back in 2 years time or 3 years time. So these technologies are becoming very cheap very quickly, and obviously that will take time. So maybe steel industry, if we all work together, we'll have some innovative solutions.
Thank you. Two questions from social media platform. One is from Facebook Live. What are the obstacles to use hydrogen in steel sector? Please explain, sir. Cost-wise, it is viable in Indian condition. And similar type of question by another from the YouTube live. What is the future of steel industry in India?
So I can comment on that first question, that hydrogen. I think I gave one statement is that if you replace 1/3 roughly coal with hydrogen, your steel production will go by double, kind of that. But that's a very gross number. It's hard to know because hydrogen production, it all depends where you are producing, where is the cheap electricity, because all these factors is the, and within the hydrogen production, as I said, 55 kilowatt hour per kilogram hydrogen. So that multiply by, if your electricity cost is, depends some places, if you can use 2 cents, I mean, I'm talking about say US cent a kilowatt hour, to anywhere it can be up to 20 cents a kilowatt hour. So that will give you the hydrogen cost. In Australia, we are talking about below 2, so $2 per kilogram of hydrogen. If you compare that, probably that will be comparable. Still, coal is very cheap energy source, obviously. I mean that even met coal is expensive than thermal coal. It is probably at least 3 times, 4 times expensive than thermal coal, but still coal is cheap source of energy. But the problem with CO2 emission, and many countries are introducing carbon tax. I don't know what's in India. In Australia, we had introduced carbon tax, although another government took it off, but there are other mechanisms. So some sort of clean development mechanism, some sort of ways to reduce CO2, although there is no tax, but emission trading scheme. So if you put the price on carbon, if you add on top of that, maybe those initially, even though hydrogen is not economic, but it will make some I would say justification to introduce slowly. That's one. Second thing is that I think technical aspect hydrogen application I'm not too familiar with, so I cannot comment too much on that. I'm more in the economics, environmental aspect of using it. So that's what I'm saying. And what's the future of steel industry? I do not have too much understanding, although I know, given my colleagues, working with my colleagues and travel in India, that India is obviously aspiring to 300 million ton a year. Still, India has got low per capita, and many countries, I think in Europe, for example, or anywhere, a lot of steel industries they are shutting down because of they cannot be competitive. So I think obviously China is a big producer. If we talk about global steel production, 50% comes from more or less China, and our Korea, Japan, they are the major producer. So, but slowly, I think cost competitive wise, India has a big future, and India potentially because it has got own iron ore. Although coal quality is not that good, but importing Australian coal with the blending, India has got big future in the steel industry. And among the neighbors also it can supply. Bangladesh has got no steel plant at all. I mean, I'm talking about integrated steel plant, but it could be big market, and it is already market. I know that, but and slowly people are middle class are growing. They are making houses. Obviously, steel demand will grow, and with the infrastructure development in that part of the world.
Okay, a lot of questions. I think 50 to 60 questions we have through social media platform. We cannot take all the questions. Just last question we are taking. The question from Manoj Kumar Biswal. Actually, he is the secretary of our local body, Institution of Engineers India, Durgapur local chapter. He asked, can renewable energy take care of power requirement of steel plant?
I don't know what's the capacity, but at the moment in Australia, for example, if I give example that our 23% energy is coming from renewables. Within probably last 3-4 years, it changed. Our renewable energy contribution was probably less than 10%, and majority of the hydro that was. But now probably 5% coming from solar. Wind is probably the next one, or maybe wind is solar wind, maybe similar capacity. So it is growing rapidly. One of our state in South Australia, their 50% energy came from renewables just last year, or maybe 60-70%. They are trying to 100% renewable because they have got large wind resources. So in India, I would say, I know that solar resources, when I looked at the map, India has got good potential. Maybe if you look at, to be honest, in South Asia, say SAARC countries, some countries have got hydro, some countries have renewable. But if we look at just one country, it would be difficult to solve the problem. But if all these countries work together, I think renewable can supply enough energy with reasonable economic sort of incentives for all the needs of the energy of the steel industry. But all these countries need to work together in that case.
Although a lot of questions left, but due to time constraint, we will send you through email remaining questions. And anybody want to ask question, they can note down our speaker's email ID, and or they can send directly to my email ID, so that I can send this question to speaker. Because now till now we have 40 to 50 questions. Okay, Then
So
thank you. I have already told that you will get couple of questions regarding the hydrogen energy, which is our interest in India now. Okay, thank you for your presentation.
so,
Over to Satadipa.
so thank you, Dr. Mondal, and thank you everyone for listening to me and bearing with me and your patience for your patience. And I'm available on LinkedIn. You can find me and send me a request.
Yeah,
I'm
yeah.
happy to
I
answer
will.
any questions you
I
may have.
yes, I will circulate your LinkedIn ID profile also
Thank
through it.
you, Dr. Mondal, and
Yeah.
good evening, everyone from Melbourne again.
Good evening, sir, and thank you so much, sir, again, Haq sir, for patiently answering all our questions and giving a wonderful talk, sir. Thank you, sir. Now we will proceed to the next part. Before moving to the next part, let me introduce our next speaker, Professor R.C. Gupta. Professor Ramesh Chand Gupta is former professor and head of the metallurgy department at IIT BHU. He was a member of a committee for environmental impact assessment for the industry in the Ministry of Environment and Forest, Government of India, New Delhi, during 2009 to 15, and a member Pollution Control Board of Odisha, Bhubaneswar, for a decade during 2005 to 15. He is an elected fellow member of IIM and IEI Kolkata. He obtained his BSc, MSc, and PhD in metallurgical engineering from Banaras Hindu University. He has a research and teaching experience spanning 42 years from 1968 to 2010 and has supervised 11 PhD and more than 25 MTech and BTech students. He operated 10 sponsored research projects with success. He has contributed in 8 books, like he has published 130 technical papers. He has delivered more than 17 technical talks in academic research and industrial organizations. His international recognitions include a chapter on energy resources, its role and use in metallurgical industries. He was external assessor for university faculty position in Malaysia and Nigeria, an invited speaker in technical meetings in Japan, Australia, and Syria, an invited author and reviewer in various technical journals. He has been judge referee for different awards. He was member of various selection committees of CSIR, DRDO, IIT, NIT, etc. Examiner for PhD, MTech in IIT universities, member of Board of Studies at PHU and Dhanbad, expert member of Pollution Control Board, Government of Odisha and other government agency. So without further delay, I would now request Dr. Gupta to please start today's lecture session.
Hello, friends. Before I move on to the main topic, I would like to say a few words about the webinar. This webinar is very timely organized. I'd like to mention that this subject was first introduced to the world in 1972, conference held at home. The
I request all
organizers in the
participants kindly
Stockholm
mute yourself.
conference were
I request all
very wise,
participants kindly mute yourself.
and they knew that what they are going to tell the world will be useless unless the information goes to the people who matter, that is politicians. So they invited not only the scientists and engineers, but also the top political leaders of the world. In that process, then Ms. Srimati Indira Gandhi, who was the Prime Minister of India, also attended the conference, and she was highly impressed by the content, and she was so much impressed that on the return home she immediately created a cell of environment, which is now full-fledged Ministry of Forest and Environment. She said then that the environment crisis which is confronting the world will profoundly alter the future destiny, and that is proving correct. Now, in 1972, there was no internet, there was no other metallurgical industries. This talk I would like to cover in four parts. The first part, I would like to answer why we should talk about energy. There I will give energy need and sources, forms of energy required by metallurgical plants, energy and environmental relationship. Then, second part, I will answer what we are doing. In this, the effort made by our steel plants to carry out the energy audit shall be presented, and we shall have a look what has been done and what more has to be done. That part 3, what we should do for future. Now it's a big problem. Here I have made I have made some suggestions. First, the possible solutions to the problems caused by energy use, and which are divided into uh, short term and long term. And second, the alternate energy sources to for the metallurgical use. The second and the last part. Now, who will do the work? That's a big question. Now, I am not aware of the world scenario, but I'm aware of the Indian scenario, and so I would like to give this details as what is the status of academic institutions in India, and to some extent what is going on in research laboratories of the country. And in the end, I'll conclude my talk. আর যে বাইরে থেকে ডিস্টার্ব করবে ওকে মিউট করে দেবে আর আমাকে মিউট করে না আমি আমার থেকে চলবে সাউন্ড বন্ধ না আমি অফ করিনি Coming to part 1, slide 3, uh, why we should talk about energy. Now in this Now, slide 4. We know energy exists in different forms, but for metallurgical purposes, we need electrical energy, chemical energy, and thermal energy. We also know that one form of energy can be converted to another form, like the chemical energy in the battery can be converted into electrical energy. The hydropower water dam converts the gravitational potential energy to kinetic energy and then to electrical energy. The chemical energy is transformed to thermal energy by chemical reaction, that is combustion over the grate. The slide 6. The energy needs for the metallurgical units are needed for three basic functions. Process function, that is to operate various equipments, we need electrical energy. Chemical functions, in metallurgical process we deal with the smelting of ores. The oxide forms had to be reduced to metallic form, and for this we need reductant, that is chemical energy. And then the last, thermal function. The all the metallurgical processes has to be provided heat energy for sustaining the various chemical reactions and separating the slag from the metal. It needs to be melted. So we require thermal energy for that particular process and also for shaping. The energy sources exist on Earth in various forms as shown in slide 7. Non-renewable energy and renewable energy. Fossil coal, crude oil, natural gas and nuclear fuels are termed non-renewable because they cannot be renewed in the lifetime of the civilization. Renewable energy sources are perpetual energy sources available on the earth like solar, hydropower, wind, ocean, geothermal, biomass and hydrogen. If we look into the energy pattern usage in the world and India as given in slide 8, what we will find that the oil, coal and natural gas, which is all part of the fossil fuel, constitute 90% uses, and the hydro and renewables constitute merely 10% of the use. These energy available on the earth are utilized for various purposes, including industry. The uh, slide 10 presents metal production, slightly older data, but it will not affect the discussion. The world produces in 2011 produced various metals, of which steel was the largest. Today, steel production exceeds 1800 million tons. The in the process for the process of extraction, we consume energy, and you will find in slide 11 that the steel requires minimum energy for extraction when compared to magnesium or aluminum. But if you multiply the production and the energy required, what you will find that steel requires highest energy in the world, which amounts to about nearly 5%, and this energy is a significant quantity and needs to be looked into. And all the energy required by metallurgical plants are in the form of a fossil fuel, coal, oil, or gas. Now, these metallurgical plants, when they use fossil fuel, they emit carbon dioxide as an end product. And this carbon dioxide joins the atmosphere, whose content in the atmosphere is continuously increasing and now is coming very close to 400 ppm. This slide 15 depicts the carbon cycle in the nature. The carbon dioxide in the atmosphere is converted into vegetation, and that vegetation is converted into peat and then into the coal. And this process of conversion of carbon dioxide to coal takes about more than 100 million years, and that is why we call it fossil fuel as non-renewable energy sources. Now, this slide 16 gives the concept of greenhouse, which is now very popular. This sun radiates energy in the form of short wavelength, which strikes the earth and gets reflected, and is reflected in the form of longer wavelength radiations, which are not able to escape to the space, but partly is reflected back by the gases present around the globe. And the various gases have different radiative capacity. As given in slide 17, carbon dioxide happens to have highest radiative capacity, 1.46 compared to other gases, and that is why carbon dioxide is treated as most important greenhouse gas. The usage of fossil fuel gives rise to increasing content of various gases in the atmosphere, as shown in slide 18. Due to this, the and greenhouse effect phenomena, the Earth's temperature is gradually rising, and mm, if you it is said that we are now approaching to a temperature of critical point where if we do not take action, it may be very disastrous for the mankind. The impact of global warming has been well discussed in various forums. It affects the weather changes, it increases the freshwater flow, a glacier is retreating and disappearing, sea water is rising, leading to loss of land in various countries. It affects the food supply and health. And so, in view of the various serious consequences of the greenhouse gases, the sustained development is needed at moment, as shown in slide 21, and that suggests the use of judicious amount of raw materials and energy, generating minimum waste, achieving increased efficiency of production by utilization of minimum amount of natural resources, cause minimum pollution to the ecosystem by adopting new manufacturing technology, conserve raw material and energy sources by reusing the product, use safer methods of production, and follow environmental regulations and control guidelines given by various agencies. Now, the slide 22 gives sustained development, suggests two methods. One is immediate with short-term targets, and second is effort with long-term target. Now, the short-term target includes energy audit of all technical process to avoid energy waste, minimize the use of fossil fuel, and reuse material to reduce carbon dioxide emission. Next, adoption and development of energy efficient technologies, and recovery and use of waste heat and materials in the process. The long-term goals include development of renewable energy sources by various for various technical purposes, develop efficient technology to have less energy use, and promote the use of renewable energy sources. So, with this, we conclude the part 1 in slide 23, that metallurgical industries are using fossil fuel to meet their energy needs. Metallurgical industries are one of the major energy consuming industry, emitting carbon dioxide as pollutant. Sustained development is needed for their existence on Earth, and energy audit is the need of the day. Coming to part 2, slide 24, what we are doing at present. In this, we shall see the energy audit of various of the metallurgical units, particularly the steel plants. The iron steel plants today can be divided into four categories. One, based on blast furnace BOF continuous casting process. Second, DRI EAF continuous casting process. Third, smelting reduction BOF continuous casting process. And then last, electric arc furnace continuous casting process. We shall look into each type of industry. If you see, there was a shift in India as well as in the world from one technology to another technology. Till 1960, the blast furnace BOF dominated the scene, and 95% plant, 95% steel was obtained from BF BOF, whereas 5% was obtained by scrap remelting. In 70s, the DRI was introduced, and by 80, the DRI plants became 2%, and by 2010, the percentage of DRI plants became 34%, leaving 45% as BOF plants. Whereas the scrap remelting plants also increased, giving 20% contribution. And it is expected by 2030 that the DRI plants will occupy the major share of steel production, that is about 60%. 10% will be from scrap remelting, and the remaining 30% may come from blast furnace process. The we shall see one by one. The BF-BOF route is totally dependent upon fossil fuel for all the activities, as given in slide 27. The energy distribution of energy use in the BF-BOF route gives that major chunk of energy is consumed by blast furnace, that is 54%, and the remaining is used for various functions of the steel plant. Now, if you look into the energy utilized and wasted, what we find that nearly 52% energy input is utilized and 48% energy is wasted in various ways. That means if we can utilize the waste energy, we can minimize the energy consumption. Now, the slide 30 gives the available waste sensible energy in steel plant in various sections like coke oven, sinter plant, blast furnace, steel making, and cast house. And efforts are being made to utilize these waste energy sources by different means. Now, let us see the energy consumption in iron making. Iron making consumes we find uh, the the global practice is about two sinter plant. Sinter plant we prepare burden uh, suitable for the charging in the blast furnace, and
All participants are
basically
requested not to share their screen.
the coarser fraction is agglomerated along with the limestone to prepare a fluxed burden, and this sinter plant, the specific energy consumption of sinter plant is for the global best is about 1.26, whereas the average Indian is about 2 gigajoule per ton sinter. The specific thermal energy consumption of iron ore pellets is also comparable to the global practice. Of course, some plants consume more. The blast furnace energy scenario, uh, a lot of efforts have been made to minimize the energy and increase the productivity of those various factors. Has been the beltless charging, use of agglomerates, coal injection, hot blast temperature, coke rate, stove, waste gas heat recovery, high top pressure, and minimizing the slag volume. The blast furnace productivity is defined by Q by K, where P is the productivity tons hot metal per day, and the Q is the coke burned ton per day, and K is the coke consumed ton per ton hot metal. Now, this gives the slide 39 gives the various parameters which affects the factor Q and K, and the Indian blast furnaces have been trying to utilize most of the factors. The difficulty is in India we have large number of small blast furnaces. The number of bigger blast furnaces are only few. The use of agglomerated burden, if you see in Indian blast furnaces, on the average of 66% compared to uh, 90% in the world. The the productivity of the Indian blast furnace is uh, lower as compared to the world. The global best is 4, whereas the Indian best is nearly 2. This is because of the raw material constraint in India. The effort has been made to cut down the coke rate as low as possible, and the present blast furnaces are running virtually on a theoretical level. The effort has been made to reduce the metallurgical coke by heating coal through tubes. And in India, some of the blast furnaces have started utilizing this practice. However, the percentage is much lower, and the average global injection is only 57 kg as compared to 250 kg in the world. The blast furnace coke rate uh, is fairly high in India because of the nature of the raw material, um, and the hot blast temperature, which is practiced in the stove, is slightly lower than the average global because of the again the refractory problem of the stoves. The many of the blast furnaces in India are equipped with high top pressure. The the average high top pressure is 1.44 uh, as compared to 2.8 mm, in the globe, 2.8 bar. The slag rate is very high in India because of the high ash content of our coal, and this is 45 kg per ton hot metal as compared to 150 kg per ton hot metal. So in totality, if you have see the specific thermal consumption of the blast furnace, Indian blast furnace, although we have a lot of constraint, but it can be compared well with the global practice. The uh, the global best gives 16.7 gigajoule per ton hot metal, whereas the Indian practice is 18.8 gigajoule per ton hot metal. Now, the slide 50 gives the various available technique for energy saving in the blast furnace BOF route, and many of them are being adopted in India, like most popular is coke dry quenching, where the coke is cooled by circulating the inert gas, and the heat is recovered heat is converted into power, and the coke obtained is also dry and of a good quality as compared to the wet process. Now, the apart from the blast furnace, the another route for steel making is the DRI, the direct reduction process, followed by electric arc melting and then continuous casting. Now here again, the energy utilized is basically fossil fuel in the form of coal or gas. The in case of gas-based process, the uh, energy utilized is much better as compared to the coal-based process, where the 71% of the energy is unutilized and wasted. The specific thermal energy consumption in coal DRI unit plants is about 30.76 gigajoule per ton DRI compared to the globe 18.83 gigajoule, which is slightly higher. The the gas-based process are virtually are fairly good in India, which can be compared with the global best. The the pattern of energy use in the coal and gas base is shown in 57, and the energy as we find that energy is wasted more in the coal based plant as compared to the gas based plant. The third method of making steel is smelting reduction, BOF, and continuous casting route. Although this method is totally new, and in India there's only one plant, and that is also not running on a full-fledged capacity. Now, This based on the Corex process, and here the the energy input is in the form of coal and oxygen, and mm, it is utilized not only for making steel but for generating power. The figure slide 59 shows the energy input that is basically in corex unit. Coming to the next part, that is electric arc furnace and continuous casting melting. This is a very popular method of reusing the scrap, and here the also the energy pattern is basically is all based on fossil fuel, because the electrical energy is in the world basically derived from the use of fossil fuel. The slide 62 gives the effect of electric arc furnace feed nature on the energy use. What we can see that the 100% steel scrap requires roughly 560 kilowatt hour per ton energy, and if we add to this DRI, 50% scrap and 50% DRI, then the energy consumption increases to 700 kilowatt hour per ton because of increase in slag. Whereas if you add hot metal and 50% hot metal and 50% DRI, the energy consumption is drastically reduced to 400 kilowatt hour energy, because the hot metal provides a lot of sensible heat. So the quantity of energy used in electric arc furnace is depicted in slide 3. It depends upon the type of feed, the proportion of feed, additional energy sources, moisture in the charge, slag and flux quality, number of charges, tapping temperature, delay between two heats, and there is a scope of minimizing energy use in the electric arc furnace, and by adopting various methods as depicted in slide 64. The slide 65 gives the various methods of saving energy by adopting different techniques in electric arc furnace melting. So with this, we can come to the conclusion of part 2, that the Indian steel plants use 100% fossil fuel energy sources. The Indian iron making units are operating fairly well in view of the raw material constraint. However, there is scope of improvement in all Indian plants. And with this example, we can see this could be true for various other plants operating in the world, uh, maybe with better efficiencies. But there is no denial that all the steel plants basically use fossil fuel, and the problem due to the carbon dioxide has to be dealt uh, for future sustenance. Coming to part 3, slide 67, we have seen that the iron and steel industry depends on fossil fuel and which is posing a problem to the world. Now, what are the possible solutions to the problem caused by heavy energy use? This we can see at two angles. One is the short-term solutions on SOS basis. Second, the long-term solutions on diagnostic basis. The short-term solutions consist of energy audit to identify sources of energy waste and its plugging. Second, the technological developments to minimize energy use, including automation. Third, utilization of waste heat. Fourth, the development of green belt to act as a barrier and sink for gaseous pollutant and dust. 5. Eco-friendly disposal of solid waste. And 6. Water harvesting to conserve groundwater and few other measures. The long-term solutions on the dance basis includes development of hydrogen as a reductant and energy source for from non-fossil fuel sources, and second, development of biomass carbon as reductant and energy source. Slide 70. Now, these are the two alternate energy sources for metallurgical use which has been thought of, hydrogen and biomass, and we shall see their suitability for the purpose. 71, slide 71 gives a picture which was concluded in the Kyoto, which is known as Kyoto Protocol, uh, that it was agreed in that the energy uses in 1985, which was there, will be taken as a base, and the world will make an effort by 2050 to cut down the dependence on coal and increase the uses of biomass and hydrogen. That was proposed in the Kyoto Protocol. But the problem, the hydrogen use in metal extraction, the source is unlimited on the globe, that is water. But the problem is how to generate it. Storing may not be a problem as we have techniques to store it as a metal hydride and use it whenever we need. The metal hydride will decompose to hydrogen and the metal. And using hydrogen for metallurgical application is well proven, and once it is available, it can be utilized fully well. The world has been making serious effort to develop hydrogen from water sources, and various methods have been tried out, including thermal process, electrolytic process, and photolytic process. They, till today, millions and millions of dollars have been spent on the development of hydrogen technologies. However, nothing has been proven successful till today. Once the hydrogen is available on a commercial basis, there will be no difficulty in utilizing it. The main hurdle of hydrogen production is the amount of energy consumed in making hydrogen is much more than what hydrogen gives back to the system. So, till we are able to solve this bottleneck problem, we have to wait. Coming next to the biomass, biomass is nothing new. In fact, the um biomass is synthesis of the carbon dioxide, uh, solar energy, and the moisture into the vegetation, which we call wood, and this wood can be burnt to uh, give energy and carbon dioxide back to the atmosphere. Now, this biomass is a proven technology and it can be stored as a wood. And wood char has been used for iron making since ages. In fact, till 19th century, the blast furnaces used wood char only, and only when the availability of the wood char was a problem, people switched over to the coke. Now, coming back to the same thing, nobody will allow the natural forest to be cut for the purpose of iron making. We have to again look into the carbon cycle, which was presented earlier. The carbon cycle, there are two cycles. One is via biomass, another by coal. The carbon dioxide in the atmosphere is converted into vegetation, and this vegetation is mature in 10 years' time and can be utilized to harness, and this will give back the carbon dioxide back to the atmosphere. This is a short cycle comprising of 10-year cycle. Whereas the cycle via coal is a longer cycle, takes 100 million years to convert the carbon dioxide to fossil coal and then going back to the atmosphere, which is not possible in the nature's civilization's time. And that is why we call it coal as a non-renewable energy source. Whereas biomass is renewable. After every 10 years, you can harvest it, just like we grow food. Every year we harvest and grow again. So on the same pattern, the energy can be cultivated and utilized. Now this figure 76 presents a schematic view of the idea. There are two parts, A and B. The part A is the present scenario where we are totally dependent upon the fossil fuel and we are generating huge amount of carbon dioxide which is going to the atmosphere, and the amount of carbon dioxide coming back to the earth's surface is very small because of various factors. One is the slow rate and the limited land available for vegetation. So the concentration of carbon dioxide in the atmosphere is increasing, and that is the present problem. Now, for the future scenario, the population is bound to increase, the energy consumption is bound to increase, and if you want to provide energy to the future generation, one has to find some alternate methods of this fossil fuel, and that to meet the extra energy sources. Now, this could be done by man-made forest, where just like we grow food, we grow plants, biomass, and after certain time we harvest it. So we establish a short-term cycle of 10 years to meet the future requirements of the mankind. Whereas the old cycle will keep continuing, and this will not decrease carbon dioxide level, but it may cause slow down or arrest the carbon dioxide growth. And at the same time, the man-made forest could meet the needs of the coming generations. Now, biomass has got some merits and limitations given in slide 77. The first thing is it's a renewable energy source. Wood char is the best carbon with the least impurity, is ideal for tropical areas and ideal for storing solar energy as wood or char. The limitation is you require land, water, labor, and an energy for forestry mechanization, and since there is not much R&D has been done, so the information about the energy for forestation is very limited in the world. If you compare the coke versus wood char, the we will find the wood char is chemically much better quality carbon, and it has very low ash content, and it has a very good energy. The only problem with the wood char is it is not strong, it is fragile and cannot be used as a lump. It has to be used in a powder form. The biomass productivity is given here, where P is the productivity tons per hectare per year. I is the solar radiation intensity in particular area, kilocalories per hectare per year. A is the area of plantation in hectares. D is the number of sunshine days in a year, that is solar exposure. And C is the energy in dry biomass, kilocalories per ton. And in this, we find there are certain species which have very high uh, yield as well as energy content, like Caesurena, water hyacinth, sugarcane, algae, and eucalyptus. The various hardwood species have been identified which have got very good calorific value and specific gravity, and can be grown in a tropical climate under various soil conditions. Now, the biomass cannot be used directly in the blast furnace as we are using coke, but it has to be injected through tubes in place of coal. So the biomass can be partly injected to cut down the coke rate. The in DRI, it can be used as a composite produce pellets, which has been experimented. And once you use DRI from the coal char, this can be converted into steel by melting into part. So we can conclude this part that the fossil fuels are the primary energy source to meet the chemical, thermal, and process needs of the metal industry. The metallurgical industry's particular plants are highly energy consuming sectors, and account for nearly 5 to 6% global share. The high energy use resulting into the short term and long term measures. Hydrogen and biomass have potentiality as future energy source for metal industries. Slide 85 is a recollection of views that we have seen so far. We have seen in part 1 that metallurgical plants need energy for operation, which is fossil fuel, and its use is contributing global warming. Part 2, we have seen that energy audit reveals that the metallurgical processes are taking measures for energy saving, but there is scope for improvement. In part 3, we have seen that the world needs to move from fossil fuel to renewable energy sources like hydrogen and biomass. Slide 86, part 4, would like to answer who will develop non-fossil fuel in India? Academic institutions, research institutions, industries. I am presenting the Indian scenario because I am more familiar with the Indian scenario rather than the world scenario. The slide 87 gives the Indian status of extractive metallurgy education and R&D. Slide 88 gives the metallurgical education in India, past and present. Before 1923, it was a family tradition. The 1923, the first department of metallurgy was established at Banaras University. Up to 1950, there were only three departments: BHU, ISC Bangalore, and Bengal Engineering College Shivpur in Kolkata. After 1958, departments were created at IITs and NITs and some other universities. And the total number of the metallurgy departments became 31 by 2016, starting with 3 in 1950. In India, we can say Pandit Madan Mohan Malviya visualized the need for metallurgy by India in 1905 while drafting BHU proposal. And Professor N.P. Gandhi established the first metallurgy department in 1919 with limited resources as requested by Pandit Madan Mohan Malviya ji. Slide 90 gives the changing pattern in the department structure. Starting with first department at BHU in 1923, there were 28 departments of metallurgy up to 1983. All were concerned with imparting education, various aspects of metallurgy. After some time, the material science departments started taking place of metallurgy, and by 2016, there were only 7 departments of metallurgy were there, and 23 departments were converted as metallurgy and material science, and one was exclusively reserved for material science. Now, slide 92 gives the change in course structure, change in teachers' interest. Slide 93 presents a graphic view of teachers' expertise in 1983. This has been compiled from publication of Indian Institute of Metals, and the teachers' interests were noted and put in a graphical form. The interest is divided into four major groups: extractive metallurgy, industrial metallurgy, physical metallurgy, and computational simulation. The teachers of IITs are equivalent are presented in shaded area. The NITs are shown in blank, and other institutions are dark color. What we can see that the density of teachers is much more in extractive metallurgy, and of course the highest number belongs to physical metallurgy, particularly in structural metallurgy, and there was none in computational science, computational simulation, because then it was not developed. Now, let me remind here that this is the period where when the extractive metallurgy was engaged in developing new iron making processes like DRI, and because of the R&D in academic institutions, the blast furnace was gradually replaced by DRI processes in India and all over the world. The slide 94 presents the same teacher's expertise compiled in 2015, information collected from the websites, and this shows that there's a shift in the teacher's interest from the extractive metallurgy to newer areas like nanoscience and simulation studies, and the number of teachers in physical metallurgy are uh, decreased, but still there. But whereas there is a considerable decrease in the extractive metallurgy area. Slide 95 reveals this more clearly. In India, there are roughly 400 teachers, and the total extractive metallurgy teachers number is 77 in 2015 compared to 151 in 1983. And this shows this presents a very grim picture, and the changing trend in academia is opposed to the growth of pattern of metal production, which is increasingly in ferrous and non-ferrous both. The slide 97 um, gives the extractive metallurgy laboratory status, and it shows that the less number of laboratories are there, and there are many reasons for that. First, they require furnaces, equipments, and funds, which is not there. Need more working space, water and power facility. Difficult to design experiment to perform in limited time with safety in laboratories, and limited manpower to get the classes organized, and less priority than many other subjects. To slide 98 presents a solution to some of the common difficulties just now mentioned. That is, first, design simple education avoid hazardous experiments in class. In some cases, go for demonstration only. To ease this, a textbook was written and published in presents the extractive metallurgy R&D in India by laboratories and industry. Uh, there are two groups. One is public sector and there is private sector. In public sector, we have CSIR laboratories at Jamshedpur, Bhubaneswar, Bhopal, and Nagpur. And with my personal knowledge, I can say the interest in extractive metallurgy area have gone down drastically in all these laboratories. The SAIL R&D, which is a very big laboratory, but is mainly concerned in solving the problems of various plants under SAIL, and I am not aware of any studies taken for being taken for futuristic uh, uh, view. The private plants like Tata Steel and JSW have big R&D laboratories, but they are devoting their energy to solve their plant problems, and I am not aware of any work being taken for developing alternate energy sources for metallurgical purposes. So, slide 100, we can come to the conclusion that academic interest in extractive metallurgy in general is declining, and energy and environmental study particularly is not visible. The public laboratories R&D are awaiting sponsors to work on topics of future interest. The private laboratories R&D are more concerned to solve their plant difficulties, and thus nation awaits for institutions or persons to take up the job for future problems in extractive metallurgy. And with this, we come to the overall conclusion given in slide 101. The metallurgical industries are highly energy intensive and generate many environmental problems. Limited studies have been made on energy audit of metallurgical processes. Alternate energy sources are needed for sustained development. Academic and industrial attention awaited to take up the challenging issues of lesser and alternate energy use. Thank you for your patience hearing. Can you hear me?
Yes, sir. Yes, sir. Sir. First question from RK Chobe from YouTube Live. He is asking, sir, you being a part of decision maker in CPCV and MOEF and CC,
Yes.
don't you feel that green technologies for iron and steel making should have separate category for EIA? Even in EIA 2020 draft proposal.
When I was there, can you hear me?
Yes, sir.
When I was there in the committee, the concept of greenhouse gases for the steel plants were not there at all. This criteria were never brought into agenda. But for future plants should be there. I agree.
Okay.
Are you satisfied?
He asked another question. Even in EIA 2020 draft proposal, no separate category for DRI making through tunnel clean, a green technology than the rotary clean.
Now, since I have left the system in 2015, it's very difficult for me to comment for the present situation.
Yes.
It should be there, but I can't make a decision, or I can't even suggest, because I'm no more in the committee.
Okay, sir. Sir, next question. What is the possibility of using biomass in DRI manufacturing through tunnel clean route if we use it as a reductant?
Technically possible, there is no difficulty. Rather, it is the only way to use the biomass. But the question is how to get biomass in large quantity economically.
Okay.
Because till today in India there is no agroforestry plan. There is only in Brazil going on, but not in India.
Okay. Uh, Another question is, will it be a substitute for anthracite coal? Actually, he added this question also. Will it be a substitute for anthracite coal?
No, anthracite coal cannot be used as a reductant because it's a very low reactivity, number one. Number two, it is not available in India.
Okay. Uh, any question from MST Microsoft team? Microsoft team, attendee
Okay.
from Microsoft team, they can raise your hand option or unmute yourself and ask the question. Simply unmute yourself and ask the question. Any participant from the MS team?
Hello, hello.
Yes,
Yes,
Can I ask the question, please?
yes, sir.
sure.
Sir,
Please.
Yeah.
Yeah.
he is Lohitendra Badu, secretary of Indian Institute of Metals, local chapter Durgapur. Ask your question, Badu sir.
Yeah.
Please.
Gupta sir, thank you very much for the nice and very informative. Lot of things we did not know, and
Thank
very interesting, sir. And particularly the challenges you have rightly thrown to the particularly the students and the research bodies here who are on the line, particularly the biomass sector. Lot of
uh,
promises there, and also the hydrogen as a reductant for the
yeah,
steel production.
yeah,
That is a great challenge. We have not been doing that still since we have been into the steel making for the last 50 years, more than 50 years. But still we have not explored these opportunities, which has a lot of promise, I believe, and which we must do rather to survive for survival of the mankind. We must do these two options. At least we some do some basic research, starting from some academia or research, pure research. We should start at least, let's say, some timeline. We must have some timeline. The previous question asked by my one of my colleagues in the YouTube. Sir, he also said, sir, you are holding a very high position. Maybe that time that kind of awareness may not be that time it was not there. But now the situation is has almost reversed. We have to we have to look after these two areas where we can do real progress in terms of research and development. That is, sir. And second thing is that sir, some data I found are old, sir, particularly the PCI injection and sale plants, other steel plant also. They are doing much better than those data. And I will say almost we have gone beyond the 100 kg mark for metal production in the PCI, GDA.
okay.
Yes.
Uh, Thank
And
you.
that
First, first thing, can I answer?
Yes, yes, sir.
Uh, Last question first. The data which I have taken was from a research book which was done, completed in 2009. So certainly the data is old, and I'm thankful that it has increased, and it should increase. Right.
yes, sir.
Uh, the, the other thing is, so far as research on this biomass and hydrogen is concerned, I already have said hydrogen utilization is not a problem, storage is not a problem. The real problem is generation. And it is a basic part where the Americans have put in a lot of effort. And the chemical means, physical means, electrical means, all have given up. The hope lies only on now bio. There are some type of bacteria and some type of algae which have been identified which can separate water into hydrogen and oxygen. And but this is only in a nascent stage. And in India, I am not aware that anybody is working on hydrogen production problem. A lot of people have shown interest in hydrogen, but real basic problem lies in the generation or the splitting of water molecule into hydrogen and oxygen. And the basic concept is the total energy required by present methods is much more than what you get hydrogen. That's why it is not coming up on a commercial basis. This is number one. Now, we leave the problem to the physicist and the chemist to give a method of hydrogen production. As a metallurgist, we are ready to use it. Now, coming to the biomass. Biomass, nothing new. We have been using biomass till 19th century. It was given up because it was not available. Now, if we come back in 21st century, back to biomass, then we cannot cut forest. We have to generate it. Now, again, unfortunately, this agroforestry falls in the domain of agriculture universities. When I started working in metallurgy department on biomass, people were laughing that how come metallurgists can talk about biomass. But anyway, the work we started way back in 1980s has come to a good scale, and one PhD was produced on the subject, and he has published more than 30 papers which are well cited on the subject. But that is not sufficient. There are a lot of things which have to be done, not in metallurgy, but in the botany department or in agroforestry department, about the mechanism of or the method of developing biomass on a larger scale. This requires lot of R&D. Unfortunately, I have tried to move in various institutes to. Hello, am I audible?
Yes, sir. Yes, sir. Continue.
Uh, am I audible?
Yes, sir. Continue, sir.
Okay, I have tried to move around certain agricultural institutes, but somehow they feel it is too far away from their domain, and nobody has taken up any interest. Apart from small groups in Dehradun, I have found who have worked on the agroforestry. So this is the area where work has to be done, maybe at the direction of a much higher authority, because it is needed by metallurgical industry. And I read an article by Mittal that if tomorrow government forces us to produce steel by non-fossil sources, then how we are going to do it? Maybe we have to use hydrogen, but hydrogen by what method? And what will be the cost of steel? Will the public will be able to bear that cost? There are so many things, and real R&D is required on two fronts: biomass as well as on hydrogen. Unfortunately, in India, there is I'm not able to count on that who has shown interest in these areas,
Okay,
particularly
sir.
in academia.
Okay, sir. Thank you, sir. Thank you. You have rightly
Thank you.
commented, sir. Thank you.
Thank you, sir. Anybody else who want to ask question? Unmute yourself and ask question. Any participant? Participant from industry? Any participant from industry?
Good evening, sir.
Yeah.
Hello.
Yes.
My name is Atif Jaz. I am from Pakistan. I am an undergraduate student of Metallurgical and Materials Engineering.
Very
My
nice.
first question is are,
Yeah. Good, good.
Can you
Yeah,
answer?
Yes, yes. Continue.
continue.
Are there any
Continue
innovations?
loudly.
Are there any innovations that might affect the cost of producing or utilizing steel that potential customers should be aware of?
First thing, the biomass is not in production anywhere in the world. So its availability is a big question. And once the availability is a big question, the cost cannot be determined. So one has to wait till this some R&D is done and it is produced on a larger scale so that it is economical to use this biomass in any plant.
Okay, sir. Have you got your answer?
Thank you,
Are
sir.
you satisfied?
Yes, sir. Okay. Thanks a
Yes.
lot of.
Thank you for question. Next question from YouTube. YouTube Live. What is the future of DRI making from mill scale as multiple growth being observed
Can you, can you
in
repeat,
last?
please? Can
Yes,
you
sir.
repeat, please?
What is the future of DRI making from mill scale as multiple growth being observed in last 2 to 3 years? And about 6 to 7 plants are coming up in Gujarat, Chhattisgarh, Punjab and Rajasthan. He is asking what is the future of DRI making from mill scale?
Yeah. First thing, mill scale is a byproduct of rolling mill, and the quantity generated is very, very small. So one can try to make smaller units, DRI units, and you can make steel, no problem. It is a very good raw material for steel making. But if you want to scale up on a larger level, you'll have difficulty because you may not be able to get that much mill scale for that capacity. That's the only problem.
Okay, but he is mentioning that about 6 to 7 plants are coming up in Gujarat, Chhattisgarh, and Punjab and Rajasthan.
Yeah, small scale. Yes, they can work on and very good. They will have profit, but big plants cannot come up.
Okay, it means for small scale it is feasible,
Yeah, yeah. For small scale is viable. Not only viable, it is economical also.
economical also. Okay. Next question. Uh, Anybody from MS team? Participant can ask question by unmuting yourself.
Evening, sir.
Yes.
Hello, sir. This
Yeah.
is Abhishek Das from. Sir, this is Abhishek Das from IIT Sarang.
It is not clear. Your voice is not clear. Again,
Good
ask the
evening, sir.
question.
Good evening, sir.
Yeah.
So this is Abhishek Das from IIT Sarang.
Yeah.
Sir, my question is that the high ash coal, which has been not used in, that is a non-metallurgical coal, which has been not used in various industries, has been thrown out, can be used for the production of gas, synthetic gas, that is a coal gasification plant. So we can see the future of coal gasification plants nowadays because as PM Narendra Modi is very much favor with this.
Uh, Non-coking coal has been used by DRI. Number one. Now, if you want to gasify the non-coking coal and then make DRI, there is a problem. Particularly the Indian coal gasification has been tried out by various methods, but it has failed. You know why? Because of the high ash and their low melting point. So we cannot go for high gasification, and low temperature gasification techniques are no good. So this is the big limitation using the Indian non-coking coal for gasification. But
Have you got your answer?
Yes, sir. Yes. Thank you, sir.
Next. Next.
Good evening, sir.
Yeah.
Hello.
Yes, yes, tell. Continue.
Hello.
Continue.
Good evening, sir. Myself Vishwajit Maja from SAIL ISP. I have a question. Actually, is it feasible for plastic waste injection for DRI steel making? And will it be helpful to increase the production?
I couldn't get it, but a lot of noise is there.
Sir, question is, he told
Hello.
the plastic injection through the tuer it is economical.
No, this is injection has
Plastic
been
injection through blast
done.
furnace tuer.
Yeah, plastic injection has been tried in Brazil. And it has not been done in India. It has been tried in Brazil, but not in India. And that too on a very, very small scale.
Okay. Have you got your answer?
In India, nobody has tried it
From
out.
ISCO steel
Hello.
plant?
Sir, sir.
Yes.
Yes,
Continue.
sir. Will it be helpful to increase the productivity?
Yes, obviously.
Unless we do experimentation, we cannot say, and we have not done experimentation in this regard. Theoretically, yes, but practically difficult to say unless you do it.
Yeah. Yes.
No, sir, in this regard, myself, Ghosh, want to ask you whether Brazil was successful in this
HOD,
effort
sir.
or not?
Sorry?
Sir, our HOD sir asking something.
Whether Brazil was successful in this effort or not? You told that Brazil has tried to use plastic. Okay. So
Yes.
whether they
On a
are
very, very
successful or not, that is my curiosity.
Yeah, they did some laboratory studies, not on a plant level.
Okay, but laboratory scale also, what they get some encouraging results or what they got actually? That is my I'm interested to know. Do you have that information?
The author says, yeah, I know the author, and he was encouraged by the results. That much I can say.
Okay. So it's not yet commercialized.
Santosh Palo is the author, and he has experimentation.
Sir, next question from Gaurav Singh. What is the future of carbon capture and storage technologies in Indian steel industries? What is the future of carbon capture and storage technologies in Indian steel industries?
In the Indian industry, they have introduced a system of carbon taxing. That is carbon credit, not tax, carbon credit. But there is what India is the audit of carbon dioxide emission and minimization, and because of that they get some credit, and that is sellable as a share in the world market. So that is going on in India, but there is I'm not aware of any industry trying to capture carbon dioxide and reuse it.
Sir, next question from our student, Miss Doita Pal. She asks, Sir, since it is not possible for hydrogen energy and biomass energy to be used as a cleaner source of energy currently, how should we approach the greenhouse gas emission problem in the Indian iron making and steel making process? Loita
I
Pal,
think
final year student.
yeah, already I have tried to answer this basic question.
Yeah, yeah.
Uh, the first thing is the audit. You must do the audit and avoid waste. Reuse the energy, number one, so that you emit minimum carbon dioxide.
Yes.
And so far as using hydrogen and biomass is concerned, it is far away because we have not yet done R&D in this direction, and it's only a proposition for future. Maybe by 2050, I can visualize there could be some hope. It takes time. R&D takes time. If you remember, DRI took nearly 20 years, 25 years to replace the blast furnace to DRI. So even if today we start working, it will take 2 decades or 3 decades. The problem is very serious and very big. So by 2050, you can think for an answer, but not before.
Okay. Thank you, sir. Another question from IIT BHU, Rohit Jha on Facebook Live. He asked, what kind of products can we recycle from steel industry waste as a secondary resource?
There are a lot of things which we can recycle from the from the industrial waste. Uh, First thing is the metal itself. Lot of metal scrap is generated, which can be recycled back in the blast furnace. In the slag, there are a lot of metal. In fact, the slag is crushed and magnetic separation is done to take out the metallic nodules and put them back in the blast furnace. Even if some slag is there, no problem, it will be separated. Then the lot of refractories are there which can be recycled in the system. The slag which is coming out can be put to use for various purposes. So there are a lot of the mill scale coming from the steel plant can be recycled. So there are various products where coming out from the steel plant can be recycled. In fact, if you see the concept of zero emission, that visualizes recycling and utilization of all the waste material coming out from the steel plant. But that requires a lot of R&D, and the young people should take the challenge for developing this.
As you already mentioned, the research are required in a process metallurgy side, which is gradually decreasing. And my next question by Jainal Abedin from IIT Kanpur. He asked, what is the future of steelmaking with the use of biochar? Biochar.
Biochar, that is biomass, same thing.
Same thing.
Biochar is nothing but charcoal, isn't it?
It is, yes. We have already
Does it mean
discussed.
already we have answered and we have discussed this.
Any participant want to ask any question? Yes, anybody?
Yes, sir. Good evening, sir.
Hello.
Sir, I'm Nandlal Sharma from Durgapur Institute of Advanced Technology and Management, Department of Chemical Engineering.
Yes, tell.
Sir, my question is that how can we implement agroforestry in India related to hydrogen energy and biomass, sir?
Agroforestry is not for hydrogen; it is for biomass.
Yes, sorry, sir. For biomass.
And the first condition for promoting agro industry is the government should look into the matter and have laws for land utilization. Our wood land is being converted converted into jungles, to the concrete jungle, that is cities. So the land is precious, and the land has to be utilized only for agriculture, that is food, and energy. So that requires a policy. Unfortunately, that policy is still not there. And in the future, there will be land is going to be under tremendous pressure, because the same land which is available has to be used for food, has to be used for energy, has to be used for living, and for everything. So that requires a very judicious and very good planning for future land utilization. Unfortunately, it is not.
Yes. Have you got your answer, Nandalal Sharma?
Thank you, sir. Yes, sir. Yes, sir. Thank you
Yes.
very much, sir.
Yes. Mute yourself. Sir, next question from Tata Steel. Very interesting question by my one of student, Neha
Yes.
Gupta.
Yeah.
Yes, you may familiar with her also. She asked, sir, is
Uh,
co-grinding of raw biomass along with iron ore flux possible before making pellets, or it requires any prior treatment?
her question is adding biomass
No,
along
sir.
with the, I don't know.
Sir, 1 minute, sir.
Uh,
Is co-grinding of raw biomass possible before making pellets, or it requires any prior treatment? Biomass, he wanted to know biomass along with iron ore and flux.
See, biomass, does she mean the raw biomass or wood char? Because biomass cannot be ground. It is a fibrous material.
Yes, yes. Seed ask actually raw biomass along with iron ore and flux.
No, raw biomass cannot be ground because it is a fibrous material.
Yes, yes.
And once you add and you heat, there is so much volatile matter coming out, the pellet will burst.
First, yes.
So it will not be useful. First, what you can do is, first you convert the biomass into char, and
Yeah.
then grind it and mix it and make a composite pellet. That's what I proposed by rotary hearth furnace, that you can make DRI by biomass as a reductant in a rotary hearth furnace or a tunnel kiln. That's a proposition.
Yes.
Already we have made experimentation.
Okay, sir. Uh, Next, anybody from my MS team, Microsoft team, participant from Microsoft team?
Hello, sir. I am Banashinga. I am studying metallurgical engineering in Salem, Tamil Nadu. My question is, what are the basic qualities to become a metallurgist, and what are the proportion of carbon in steel making, sir?
Please, can you please repeat the question? I couldn't get you.
Please repeat your question again.
Sir, what are the basic qualities to become metallurgist, sir?
Okay. Another one is question is
What is the percentage of carbon in steel making, sir?
what is the percentage of carbon in steel making?
Yeah, you are asking a very, very
interesting
basic question. Yeah, good. The steel is alloy of carbon and iron, right? So if the carbon content is less than 2, we call it steel. And if it is more than 2, it goes in the domain of cast iron. That is a simple definition, number one. Yeah, the first question was what qualification is required to become metallurgist. Well, you should only have a bill to become metallurgist. Anybody can become metallurgist, and by proper training, you can always become a good metallurgist.
Thank you, sir. And another question is, will you allow other college students to attend your college international webinar training program like that, sir?
You ask the coordinator, Mandal.
Yes,
Mandal,
yes. In future webinar also we will invite you and your college. Okay. Because in present webinar we have near about 800 participants. Therefore, we closed our registration period 2 days before that time. Okay, in future we will think about it. Next question, anybody, any party? Any participant?
Arup, I
Any
think there is no more
participant?
question. So
No more question. If no more question, then we will go for closing. Yeah, some 1 minute.
some
No,
no.
no. I think there is no more question. Then thank you, Professor R.C. Gupta, for sparing valuable times and in such age also. Thank you, sir. Uh, and I am handed over to Satadipa.
Thank
Satadipa,
you, sir. Thank
continue.
you so much. Yes, sir. We have had a wonderful evening, and this was really a very successful webinar. We have taken up such crucial topics, and we are doing these webinars in this COVID-19 situation. So now, in the hope that we'll do these kind of webinar as long as the lockdown is still on, and then we'll meet physically after that, and we'll have the sessions that we already had, and we miss them so much. So now I would request our HOD sir and our coordinators to please close this webinar, officially give it a closure. It was a wonderful experience. Thank you so much.
Thank you, everyone.
Thank you everyone for attending.
So before I make the official declaration of official closing, I want to thank the speakers, the dignitaries in the inaugural ceremony, all the participants, and above all the persons who are there behind the curtain, the students who made a great effort to make this kind of webinar successful, and the interest that was shown in term. I have seen the questions of the participants' interest in this area. I think it will promote our country to achieve the target. So it's very good sign that young people are also very interested in this field. And I will request all the participants, our effort to make such kind of programs on the emerging areas will continue. There are several plans in future, maybe in a coming month or next month. Please keep on watching the institute website for future such events and register. With this hope, I make the announcement of the closure of this ceremony.
Sir, before
Thank you
sir,
once
before
again.
1 minute, sir. 1 minute, sir.
Yeah, one announcement that
Before closing, I
Arup
want
want to
to,
make.
yes, actually,
Mute yourself, sir.
yes, after filling the feedback form, you will get the certificate. Okay. Therefore, all participants are requested to fill the feedback form, which will be circulated soon. Okay. And over to HOD sir. Sir, unmute yourself. HOD sir.
So what Arup told, I just want to repeat. Please fill up the feedback form that will be sending soon, and that is mandatory. Otherwise, basically the e-certificate that will be issuing is linked with the feedback form. If you don't fill up the feedback form, you will not get the e-certificate. So it is a must. Please, we'll be sending the link soon. Or could be Arup Kumar Mondal will be sending the link for feedback. Please fill up the feedback. It's very short form. and get the e-certificate. I thank you once again, all of you, for joining this program. Thank you.
Thank you. Thank you. Thank
So,
you.
Tata.
Thank you, sir.
Tata, bye.
Thank you, Valu sir.
Thank you.
Thank you, sir.
So, we're
Thank
going to
you.
log out.
Thank you, sir.
Tata, Tata, bye bye.
Thank
Thank you, sir.
Thank you very much, sir.